A confirmation about the audio, please, guys. If the audio is clear and available, kindly confirm. Thank you. Kishan, it is generally very difficult to score in GS3 because of the type of questions which are asked. And there are also a lot of variables when current affairs comes into the picture. There are many areas where you need to end up interrelating with the portion of the static, the main subject that you have studied. Now, many of the candidates, when they study, they will study current affairs separately. So if a question associated with current affairs is asked, they will directly address the overlying cause. They will not address the base of it. And that basically fetches you very little marks. If, however, when we read current affairs, that is why newspaper reading is suggested rather than drawing on some gist somewhere. So if you go for a detailed newspaper reading, you gain a lot of perspective about any issue of current affairs also, and that first hand experience of getting through it, that helps you interrelate with the portion of any static subject that you would have studied, be it environment, be it agriculture in geography, or even science and tech. So that is why in general. Yes, Shashank, majorly this will be asked, the landforms majorly are asked in the prelims only. Okay. So, hello, a very warm good morning to all of you, and let us initiate the discussion for another portion and another module of geography. So, yesterday we were talking about the portion of climatology, and we had initiated the discussion where we had talked about what do we understand by atmosphere, what are the components of atmosphere, the role played by each of the components of the atmosphere. Now, slowly and steadily, as we will study the portion of climatology, the role played that we have studied, that what is the role played by individual components, that will get much more clearer, and that impact and that concept will get much more deeper as and when we study the different phenomena. Then we looked at the modes of heating, the modes by which heat is transferred. We looked at that first of all, it is the solar insolation which heats up the surface, and thereby solar insolation, or rather the solar rays, they travel by the process of radiation. And after that, once the Earth's surface is heated, that is when they start emitting their own wavelength, that is terrestrial long wave radiation, as it is referred to. And that is when, if you have the presence of greenhouse gases, in that case, some of that terrestrial radiation is re-reflected back, causing the warming and heating of the Earth's surface. Otherwise, that heat is lost out into the space. We also looked at what is advection, a process of heat transfer. We looked at the concept of lapse rate. We looked at the concept that what is the environmental lapse rate and how lapse rate differs when we talk about a moist condition or when we talk about a dry condition. And then eventually we had discussed about the adiabatic process. That what do we understand by adiabatic cooling, adiabatic heating, all of that which is initiated as a result of expansion and compression of the air. Whenever air is allowed to expand, normally and naturally its energy level goes down and it starts to cool. Whenever an air is compressed, thereby we have seen that it ends up shrinking, and that is where the energy level increases, increasing the temperature in that area. So these are the portions of climatology that we have already initiated and we have done the discussion about. So today we basically start with the portion here we start with the portion of atmospheric structure. So we start with atmospheric structure, and then after that we shall be moving ahead into the factors of insolation and the factors which contribute to temperature variation across the planet. Lapse rate is the rate at which the temperature changes as you move up in height. So it can be positive, it can be negative, it can also be zero. That means the temperature can rise up as you move up in height, temperature can fall down as it naturally happens in the region of troposphere, or temperature can remain constant as we will see later on. So that is lapse rate. Okay. So now we initiate the discussion about atmospheric structure. So when we talk about atmospheric structure, so the atmosphere that we see around us, that also is arranged in various layers. Now, why do we know, or why do we say layers, and how do we get to know that it is arranged in the set of layers? Because as you move higher up in the atmosphere from the ground surface, after a particular height, you will come across sudden change in the temperature conditions, and that will change again after you cross another particular height threshold, which gives you an idea that this might exist as a different layer altogether. Now, all these layers, they have their own unique properties that they are able to exhibit, all of them. So let us take a look at these particular layers. Let us try to understand what is the behavior that we observe there. Okay. Now, before that, let us talk about one basic concept, and that is the vertical rise of air or vertical movement of air. So, whenever, let's suppose the ground surface. Now, if suppose I consider a parcel of air, before going to that, let us attack the very basics here. Now, let's suppose here this is a gaseous molecule, a gaseous particle, and let's suppose I'm heating it up. I end up heating this gaseous parcel or gas parcel, whatever you want to call it. When I heat it up, then this will end up gaining some amount of energy. This air will gain some amount of energy, as a result of which the particles will start moving. Some of the particles might even leave the system, might even escape. So, when I have heated it up, the air, what do you think? Will there be a change in the weight of the air parcel? Will it remain or exhibit the same weight? Will it become heavier? Will it become lighter? What do you think when you heat it up? Perfect. So it becomes lighter. So heating of or warm air is lighter. And when warm air is lighter, anything, let's suppose this has got heated up. This air parcel has gotten heated up. So it becomes lighter than the surrounding. So then what will happen? It will rise up, right? Why will it rise up here? Why do you think it will rise up? Because the air above it is cold, right? The air above it is cold. So all around it in this region also, the air around it will be colder, cooler air. So with this, can we say that air rises up as long as it is warmer than the surrounding? We can say this, that air will rise up as long as it is warmer than the surrounding. And that also ends up meaning, for example, in a region where you have, let's say, negative lapse rate. Negative lapse rate means if you have negative lapse in this case, it means here you have colder air and here you have warm air. That is negative lapse rate. Negative lapse rate is what? That if you move higher up in altitude, the temperature actually ends up increasing. That is negative lapse rate. So in the case of negative lapse rate, would we observe the vertical movement or the vertical motion of air? What do you think? Will the air tend to rise up? No. In this case, you have cold air at the bottom and warm air is at top. So whenever you have a positive lapse rate, in those areas, you will always end up experiencing that warm air, which is at the bottom, always tends to rise up. So always, this is mostly experienced in case of positive lapse rate. Okay. Now, with this principle, let us initiate the discussion of the different layers of atmospheric structure. Let us get an idea where we have this vertical movement of air, where do we have the positive lapse rate, and where is it that we experience a kind of a negative lapse rate. So here overall you will observe that different places or different portions of the atmosphere, they are arranged in various layers, and that is important or relevant because majority of all the climatic conditions that you observe, majority of the atmospheric phenomena that you observe, that is restricted into the lowest layer, that is the tropopause, or rather troposphere. Then after that, you have supersonic planes moving into the region of stratosphere. Then you have the northern and the southern lights, that is auroras. They are created a lot higher above. So the property ends up changing as you move up from one region to another. If you observe the temperature, observe that the temperature decreases, continues to decrease as long as you are in troposphere. And then suddenly in the stratosphere, the temperature starts to increase. Again, as you enter into mesosphere, the temperature will reduce. And then again in thermosphere and exosphere, where the air density is almost non-existent. Air basically exists in clumps and chunks, air molecules. So there again, the temperature ends up increasing. So let us take a look at all of these layers first of all, starting with the troposphere and the tropopause. So when we talk about troposphere, it is the layer closest to the Earth's surface or the layer hugging the Earth's surface, the lowest layer of atmosphere, that is troposphere. Now, yesterday we had discussed that the density of air is going to be maximum closest to the ground surface. And the reason for that high density is going to be gravity. Because the gravitational pull is going to be so very high, that is why majority of the water particles, dust particles, or water vapor rather, all the gases, they start hugging the ground surface. That is why almost 80% of the mass of the atmosphere is to be found in the region of troposphere itself. But then the height of this troposphere, it is not uniform, it is not fixed across different parts of the planet. And why is that? You will observe that height of troposphere is significantly higher around the region of equator and is particularly lower around the region of the poles. Now here, average height is 13 kilometer, where around the poles, the height of troposphere is around 8 kilometer, but around the equator, it is at 18 kilometer. What is the reason for this? So there are a couple of reasons involved here. Let us understand them. So, reasons for the variation in height. First reason. Now, we can think about air or atmosphere as a state of matter in itself. We can think about a mass of air to behave like a state of matter. Now, upon heating any state of matter, it tends to indicate an expansion, and upon cooling any state of matter, induces a rate of slight compression, contraction in general, isn't it? So, around the region of equator, because the amount of heat in general is higher, that is why the air you will observe tends to expand a bit. So, around the region of the poles, because the temperature is very, very low, there is a slight contraction which happens. So, first is the thermal expansion of air at equator. Okay, and thermal contraction at poles. Now, the second factor. So, we have also seen that the air, when it gets heated up, it initiates a kind of a convection current. We have seen that. Now, when let's say an air parcel gets heated up, there will be a convection current. That is how it will end up transferring heat. So, any convection current will have a rising column. Any convection current will have a sinking column as well. So, if here you have a convection current whereby the heat is transferred by the air into the upper atmosphere, now you will observe that when it is getting heated, that is where the air will rise up. So around the region of equator, the air gets warmed up and rises up. Now, this rising column of convection current oftentimes pushes the height of troposphere upwards, whereas around the region of the poles, you have the sinking portion of the convection current, and that is where it brings down the height of the troposphere around the region of the poles. So here, convection current. So rising column at equator enhances the height or increases the height, whereas sinking column brings down the height. In polar area. Okay. Now, why that convection current is initiated? That convection current is initiated. If you remember, if you recall yesterday's session, we had discussed about one of the methods of transfer of heat, that once the ground gets heated up, the warm air rises in the form of or in the process of convection, and that is where it transfers heat to its surroundings. So similarly, when you will observe the warmer air, that warm air, let's say when it gets heated up, it will end up rising. Now, as it rises up, it will tend to push upwards here. And that is where oftentimes the height of the troposphere is increased. Whereas this convection column will also have a sinking current at the region around the poles, as we will study with the air circulation. Because generally, when you have a convection current, colder portions they come down. So that is where around the region of the poles you have the sinking portion of the convection, which is going to bring down the height. Now there is another minor factor which is involved. not very major, but a minor factor nonetheless. Now, that is accrued to the shape of the planet. The shape of the planet. Now, as the planet continues to rotate from, let's say, west to east, right, there will also be a centrifugal force which will be acting. What is a centrifugal force? Force acting away from center in a rotating object. So any rotating object, any object which continues to rotate, it experiences a force away from center. That is a centrifugal force. Here also, as the planet is rotating, there will be a centrifugal force experienced around the region of equator, right? And that force will be acting outwards, isn't it? That force will be acting outwards. Now imagine if you have the parcel of, or if you have atmosphere, if you consider that atmosphere to be rotating across along the planet. Now what will happen? Here the air will also get pushed. As a result, it will develop a kind of a bulge here. The atmosphere will develop a kind of a bulge, isn't it? And that is why you have a slight bulge in the height of troposphere around the region of equator, where that centrifugal force is significantly high. So the other reason will be centrifugal force acting at the region of equator. Centrifugal force acting at the region of equator, there also you will experience this. Okay, so that is basically what you come across as the reason, all the reasons why troposphere is significantly thicker around the region of equator and troposphere is significantly thinner around the region of the poles. Okay, so that is where you have this particular aspect. Centrifugal force. Okay, see guys, centrifugal force is okay, let me try with another aspect. This is the planet. Okay, this is a planet which consistently is revolving from west to east. So this is the center. We can say that the planet is consistently rotating around the center from west to east. So around everywhere across the planet, you will have endless amount of circles indicating that particular region. Endless amount of these circles can be drawn indicating that particular region, isn't it? Now, when we think about the centrifugal force which is acted due to rotation, that centrifugal force will be quite significant and maximum around the region of equator. It will be acting in the outward direction, and that outwardly direction of action of centrifugal force that pushes the atmospheric layer outwards in this region. In both these areas, it pushes the atmospheric layer outwards. That is what you experience. So that is what is experienced as the reason for the difference in height. Now here, if you think about it, in this region of troposphere, Deepak, that is what I had tried to explain by this image. Your question I understood. Your question is, but the earth is not rotating around equator, so how centrifugal force is acting at equator? If you take a look at this image, Deepak, and notice this very carefully, if you take a note of this particular image, here any portion at equator, it will be moving across around this circle. Similarly, if you have any point in this region, it will be moving around this particular circle. So if I talk about the rotation of the planet from west to east, Can I not say that around the region of equator, it is moving around this central point, the center of the planet? So as it is moving around the center of the planet, will there be a centrifugal force acting? There will be. And that centrifugal force will be acting in what direction? Outward direction around this circle, everywhere in outward direction, isn't it? So that will push the air significantly. Now, the argument might be that this centrifugal force will be experienced in every place. Yes, but the aspect or the quantity of centrifugal force will be very different. Okay. Munna, according to these reasons, air density at pole may be higher than that of equator. It always is. Okay. So now, after that, radius at poles is lesser, so why force is lesser? Because the speed of rotation is very little at poles. It reduces to zero as you go to the region of the poles. Now, after this, we come to another layer. Before that, when we talk about troposphere, what do you think? Here, will you experience a vertical rise of air or vertical movement of air? Will it be observed here or not? What do we think? Perfect. So here, significantly, the when we talk about troposphere, here you will always come across a kind of a vertical movement of air. Air will rise up when it is heated, air will sink down when it is cooled. So there is a consistent mixing which keeps on happening. Now then we come to the next layer, that is referred to as the stratosphere. Stratosphere is the layer immediately above troposphere. So, in the case of troposphere, the temperature decreases as you move higher up. It might happen that by the time that you are at the top of the troposphere, the temperature might be anywhere in the range of -60 to -70 degrees Celsius. It can easily attain that temperature because in that entire area, it is going to experience a kind of a positive lapse rate. That means temperature will continue to decrease as we continue to move higher up. Now, then we come to the portion of stratosphere. In stratosphere, things change ever so slightly. In the sense that in the case of stratosphere, you will observe that for a distinct particular portion within the stratosphere, you have the concentration of ozone gas in a very distinctly thick layer. You have a concentration of ozone gas. This is what is referred to as ozonosphere. Okay. Now, this ozone layer has got a very specific role that it plays. Now, this ozone layer, what it does is, when you have ultraviolet rays which fall upon it, ultraviolet rays of the sun, when they fall upon it, thereby these ultraviolet rays, they are absorbed and are reflected back. It is a property of the ozone molecule in itself. Ozone molecule is nothing but oxygen atoms in a different state. So you have O3 that is represented as ozone molecule. So here the ultraviolet rays of the sun, they are absorbed and are reflected back. Now these ultraviolet rays, they also have significant amount of energy. And when they reach the Earth's surface, they have a particularly damaging impact, not only on us humans, but also all around us in terms of biodiversity, in terms of the plant life, in terms of marine productivity. So ultraviolet rays will have very detrimental effect. Now, these ultraviolet rays, overall, you will observe that they are reflected back, radiated back from the ozonosphere. They are absorbed and they are not allowed to come to the Earth's surface. Now, majority of the ultraviolet rays, they will end up heating this portion of ozone layer quite significantly. As it is observed or absorbed, the UV rays will end up raising the temperature quite significantly. So in this, as we move higher up, temperature marks an increase. As we move higher up, temperature marks an increase because of warming of the ozonosphere. And because in this region, for example, this ozone layer also starts acting as a kind of a heat source, it ends up transmitting a lot of heat in the upper layer. A lot of heat is concentrated in that upper layer also, because that is where the ozone ray or the ultraviolet rays, they spend significant bit of time being absorbed and being reflected. So it is in this region of stratosphere where we will come across a unique situation where the temperature increases with height. And that is what is referred to as a negative lapse rate. So in this case, temperature increases with height. And that is negative lapse rate. Okay, that is something that you observe here. Now here, negative lapse rate means what? It means in a particular region, warmer air is at top and cold air is already at bottom. We know that warm air is lighter and cold air is heavier. So in this case, what do you think? Will there be a vertical motion of air which will be observed? Or will this portion lack any vertical motion? Very good. So in this region, you won't observe vertical movement of air because the warmer air is already at top, colder air is already at the bottom. So that is why you have very weak vertical motions in these areas. Only in very rare scenarios will you find a rising air column in this area. And there are a lot of different atmospheric phenomena which needs to come together for the air to rise up in the region of stratosphere. This is the reason why when we talk about larger commercial airliners, that is the ones which go for intercontinental travel, the larger planes that you have, they always end up flying through the lower region of stratosphere. Why? Because in stratosphere, because there is no vertical motion, thereby as the airplane is flying, it won't experience that turbulence. Because when an airplane is flying, if you have a rising air column or a sinking air column, turbulence is experienced by the airplane. That can be oftentimes disturbing. So for the smaller airplanes that you use, let's say for domestic travel here and there, when you move from, let's say, Bombay to Kolkata, Delhi to Bangalore, and so on, they can move in the region of troposphere itself, the lower regions of troposphere. But when we talk about the larger jetliners, they end up using this lower region of stratosphere. Now, let us analyze something here. When we have talked about the region of the surface, we have, let's say, the troposphere. End of troposphere is marked by a very thin layer which is referred to as tropopause. So here you will have tropopause, very thin layer, and then you have stratosphere. This is stratosphere, this is troposphere. Okay. Now, as we move higher up in the region of troposphere, the temperature tends to decrease, isn't it? So, at the top of troposphere, can we say that here you will have very cold conditions? in this particular area, we will end up exhibiting very cold conditions in general. We can say that. Now, in the region of stratosphere, we have warming, right? So here, can we say we have hotter air? So now when you think about the region of tropopause, that tropopause, this is the region of tropopause after all. So here, we can think about the tropopause as being heated from above and being cooled from below. So if let's say XYZ was the, or X was the temperature of the tropopause, whatever X. So it is being heated from above, it is being cooled from below. So what do you think? Will there be a change in temperature of X? Will the temperature remain consistent? Will it increase? Will it decrease? What do you think will be the impact of temperature here in tropopause? Beautiful. It will be stable and it will be consistent because you have both the impact of cooling and heating happening over a very thin layer. So there, as you travel through the region of tropopause, you won't experience any sudden rise or fall in temperature. That is why tropopause exhibits a zero lapse rate. No change in temperature with change in height. Of temperature with height. And why? Because of impact of heating from above and cooling from below. Okay? Cooling from below, in the region of tropopause, there is cooling which is carried out. And from the region of stratosphere, there is heating which is carried out. Hence, there is maintenance of temperature, and the temperature doesn't indicate a change with height. That is why tropopause indicates a kind of a zero lapse rate. Now, when the stratosphere is getting heated up, so that stratosphere is getting heated up due to ultraviolet rays. Now, think about it. Now, this becomes a source of heat in a way, this entire region of stratosphere. This entire region becomes a source of heat. So, for the layer of air above stratosphere, that is the mesosphere, the source of heating will be the impact of stratospheric heating. So, again, in the case of mesosphere, let's suppose we have the region of stratosphere underneath. And on top of it, you have the mesosphere. So, as we move higher up in the region of mesosphere, can we say that we are moving away from the source of heat? Source of heat being the stratospheric warming, right? So, as you move higher up in the mesosphere, the temperature will start indicating a drop. So, here again, as you are moving up, the temperature is decreasing. Why? Because you are moving away from stratosphere being the heat source. So that is where here again you will experience a kind of positive lapse rate. Now, do you think here, when we talk about this as the positive lapse rate, Now, do you think here vertical motion will be observed in the air, or here also no vertical motion will be observed? What do you think? It will be observed, right? So that is where here also vertical motion, strong vertical motion of the air will be observed. So look at it, temperature starts decreasing with the increase in altitude, and temperature can reach even minus 100 degrees Celsius up to a height of around 80 kilometer. Now, heat is dispersed upwards by the vertical motion. Significant amount of vertical motion is observed. Mesosphere, in fact, is one of the least known portions of the atmosphere because it is in that awkward height where the satellites they fly above it, the high altitude supersonic weather related aircrafts and weather data gathering aircraft they flow below it, so thereby you don't have many specialized flying objects which move through mesosphere. That is why we know very little in detail about mesosphere. And sometimes what is done is, with the help of sounding rockets, experimental rockets, it is launched, and some or the other aspect of mesosphere is tried to be understood. Then beyond the region of mesosphere, as we move up, the density of these gaseous molecules that starts to waver. The density of the gaseous molecules that starts to change. Maybe in one area you will find a large density of nitrogen, in certain another area maybe large density of oxygen, in certain another area maybe few atoms of oxygen and nitrogen out there. Now that is where it has got a kind of an uneven distribution at greater height. Eventually the air particles they start to dispense out. You will not find larger presence of these air molecules or the gaseous molecules, and eventually they will disappear into the outer space. So that is the region of thermosphere and exosphere. In the region of thermosphere and exosphere, the temperature of each of these particles is very high, because at each of these regions of the particle, the unadulterated rays, that is the X-rays, etc., of the sun, they end up hitting. So that is where, wherever you try to feel the temperature, it will be very, very high, even though that air density in itself will be very limited. However, when we talk about these air particles existing in various different chunks and various different portions, now when they are bombarded with the unadulterated solar rays. Unadulterated solar rays means that the impact has not been lessened as it is traveling through these dense layers of atmosphere. So on top of mesosphere, you have the unadulterated solar rays which hit these gaseous particles. And that is where oftentimes, due to the energy of the solar rays hitting, the electrons sometimes they jump the ship, and that is what gives rise to charged particles in that region. And these charged particles they are referred to as ions. Now here you have the presence of significant amount of ions, and that is why the region is referred to as ionosphere. So that is as simple a concept as, if you have, let's say, an atom of oxygen, it is hit by a lot of energy of the solar waves, and including ultraviolet rays, including X-rays, everything is hitting that. As a result of that, the electron simply will jump ship, or maybe there will be another electron floating around which shall be added up. That is where the gaseous particle goes into a charged state, and that is an ion. Now, to give you some more information about it, sometimes when these gaseous particles which have become charged, when they revert to their original neutral state, either by an electron rejoining them or the excess electron leaving them, that is when they end up emitting light. Okay, that is when they end up emitting light. And that is the source of the northern and the southern lights that you observe closer to the region of the poles, what are also referred to as auroras. You have the aurora borealis in the northern hemisphere. You have the aurora australis in the southern hemisphere. So that is how these gaseous particles, they end up producing significant amount of light also. Now, here, the presence of charged particles in this layer, that also allows radio communication to happen. Without the presence of charged particles here, radio communication cannot be carried out. So, how is it? So, these charged particles, they re-radiate or reflect. Basically, all these charged particles, they reflect the radio waves which are received by a receiving station, for example. So, suppose let's say we have the ground surface, and here let's say we have the transmitting station, the ionosphere. You have the presence of charged particles, and they are randomly distributed. Okay. Now, as the radio waves are, let's say, emitted, radio waves are emitted. These radio waves, they will hit these charged particles and they will then get reflected back because of the presence of charged particles and nothing else. Now, they will get reflected back, and that is where they will be intercepted by the receiving station. And that is how we end up experiencing a kind of radio communication overall. Now, that is how radio communication used to be carried out, and radio communication was very prevalent some time back. Now you have satellite communication, so this factor is not involved anymore. But this is where the presence of charged particles in itself would ensure the reflection of the radio waves. Now, sometimes what you would have experienced if you have not used a radio set, if you ask your elder generation, they would have experienced that when you have a cloudy condition, when you have development and the presence of very dense and thick clouds, in those conditions, what happens is that the radio simply doesn't catch a signal, or the radio catches a signal of a new station altogether or a different station altogether. So, why does that happen? That is because when we talk about the clouds also have a property of charge. That is why we experience thunder and lightning. We'll study that how clouds gain charge at a later stage. But these clouds, they also have charge. So let's suppose in this region, you have the presence of clouds. Now these clouds will also have some charge. Now these will start reflecting it back. So what was to be received here is now bouncing back here. That is why during cloudy nights, the region of, or when we talk about radio communication, during cloudy nights, radio communication used to simply got awry or would not function significantly. Why? Because a cloud field would interfere in the transmission of the radio waves. But otherwise, ionosphere, purely by the presence of charged particle, facilitates this kind of a reflection of the radio waves. Okay. Now, after this, we come to insolation and temperature. Before that, we'll take a couple of questions. So, why stratosphere is the source of heat for mesosphere? Why not direct sunlight? So here again, please understand sunlight is also a source, but a major source is that of stratosphere. And that is because it is consistently, the mesosphere is consistently sitting atop that. So there is again that entire process of conduction and being in contact. So that again induces heat. In fact, up till the region of mesosphere, the atmospheric composition is quite uniform. So as the atmospheric composition is very uniform, that is where it is referred to as a homogeneous atmosphere. And beyond that, beyond the layer of the region of mesosphere, you have heterogeneous distribution of air, so heat transfer is not efficient. But up till the region of mesosphere, you have a common distribution and a uniform property of air. That is why homosphere or homogeneous region. I still not getting why troposphere has zero lapse rate. Troposphere doesn't have zero lapse rate, so it is good that you are not getting that. Troposphere has got a positive lapse rate, my dear friend. Please understand, troposphere doesn't have a zero lapse rate. It is a tropopause which has got a zero lapse rate. Nisarg, in troposphere, there is vertical motion of or, which means warm air rises up. Then how do we have colder air in tropopause? Okay. A very innocent question, so to say. So imagine if this is the ground surface, if the air is rising up, this air is rising up means what? And listen to this carefully, Nisarg. That means, will it expand as it rises up? It will expand. Expand means it will cool down. Let's say, let's observe, or let's have a kind of an assumption that this rise is going to experience a lapse rate somewhere around 5 degrees Celsius per kilometer. 5 degrees Celsius or 6 degrees Celsius change per kilometer, right? Suppose the temperature at the ground surface is 40 degrees Celsius. Do the calculation. 6 degrees Celsius change per kilometer. The height of troposphere around equator is 16 kilometer. Okay. So what will be the temperature at the top of 16 kilometer? Let me know that, Nisar. What will be the temperature at the top of 16 kilometer? It will be close to around, yes, minus 56 degrees Celsius. So now do we understand why the temperature will reduce? Or do we still have doubts? So that is why just beneath the region of tropopause, you have very cold air which is present. Okay. Unadulterated sunlight, Raghav, basically means the sunlight which is not, or some portion of it has not been dissipated in the dust particles, has not been dissipated by the ozone layer. It is where the sunlight above mesosphere will have the X-ray components, the X-rays. We know how damaging the X-rays are. So X-rays will be there, UV rays will be there, all of this, infrared rays will be there. So all of that will have very high amount of energy. Okay. How tropopause have zero lapse rate? Okay. Tropopause has got, so looking at the questions that I see, I have questions that why temperature decreases in troposphere. I have questions that why temperature increases in stratosphere. I also have questions that why mesosphere is colder than stratosphere. I have also questions about tropopause and the lapse rate in tropopause. So in a way, you want me to repeat the entire thing which I have already repeated significantly. So there, any of you who, let's say, have joined late, and we are able to see when you join late, we get an idea when you have joined. Any of you who have joined late, rather than expecting a complete repetition, please understand you have the recordings with you, which you can watch at your own leisure time. So talking about the region of tropopause, why is it tropopause indicates a zero lapse rate. So tropopause indicates a zero lapse rate. Zero lapse rate means there is no change in temperature. So here, let's say the temperature of tropopause, let's assume the temperature of tropopause is around minus 60 degrees Celsius. Let's assume. Now minus 60 degrees Celsius is the temperature. Now this air parcel, it is a thin layer, very thin layer. Consider this air parcel as a state of matter. Now this air parcel is being cooled from below, is being heated from above, right? If suppose this is the pen, I'm cooling it from this region, I'm heating it from this region, will the pen indicate a change in temperature? Won't they nullify each other? So that is why tropopause in general, because it is being cooled from below, heated from above, that is why it exhibits a consistent temperature. Okay? Is that understood? Thickness of tropopause, it is very, very thin, sometimes even so marginal. In many areas, it can be a few meters or a couple of kilometers thick at max. So the one who had asked the question, is that clear? Kindly confirm. Once you are asking a question after explanation, kindly confirm. This was a question by Lakshmi. Is that understood? Fair enough. Height of ozonosphere, Tajinder, is generally in the range of 20 to 50 kilometers above the Earth's surface. Why charged particles are not present in the region of mesosphere despite sun rays entering this layer? So sun rays, my dear friend, enter even the region of stratosphere. They will enter even the region of troposphere. So when we are at a greater height, that is when the impact of these solar rays, they are maximum, and that is where they will start hitting the particles individually. When we come to the region of mesosphere and below, you have a homogeneous formation of the gases, and that is where formation of these individual ions, that is not possible. That is where its impact is significantly lessened. That is the reason why ionosphere lies above mesosphere. Is it only convection current so we have high difference in troposphere? No, absolutely not. We have two other reasons also that we have discussed. Formation of ions in ionosphere is because of the bombarding of those gaseous molecules with very high amount of energy of the solar rays. That is why you have the presence of ions. Okay. Ionosphere exists beyond the region of uh, mesosphere, in the region of the thermosphere in general. Is it important to which ions present in ionosphere? Which ions present in ionosphere, as in you want to identify which molecules are present? So you have oxygen and nitrogen molecules which end up forming these ions. Okay. And heating leads to expansion or contraction. Think about it. Heating will always lead to expansion of material. Always heating will lead to expansion of material. Okay. Now, here, when we talked about the various different portions of the atmosphere and their phenomena, so after a particular height, beyond the region of ionosphere, that is where we experience the presence of auroras, the northern and the southern lights. Now, they also end up happening at high latitudes closer to the poles. That is where the charged particles from the sun, they end up hitting the top of the atmosphere. And when the charged particles of the sun, they hit the molecules of oxygen and nitrogen, they end up causing an electron to leave. And when that electron rejoins these atoms, light is produced. And that is where light is produced in the higher latitudes. So why is it that these are produced only in higher latitudes? Why not over India? So this has got to do with the magnetic field lines of the planet. So when we talk about auroras, here they are created by the charged particles from the sun. Charged particles from the sun, they continue to hit. Now, these charged particles, they will concentrate where there is greater concentration of magnetic field lines. So when we talk about the magnetic field line, around the region of the poles, you have a high density, a high concentration of these magnetic field lines. So it is because of this reason that you will find that majority of the charged particles from the sun, they end up concentrating around the region of the poles and at higher latitudes. And when these charged particles, they hit the region of the poles, basically they are hitting the top of atmosphere, and the oxygen and the nitrogen gaseous molecules which are present there, they will interact with these charged particles from the sun, and that ends up emitting light, which we refer to as aurora borealis in the northern hemisphere, aurora australis in the southern hemisphere. Typically those are the regions. Okay, now, yes, in Ladakh, but it is a very rare phenomena. It is sometimes these charged particles might end up penetrating to this, coming here and there. So some areas you might get to look at it, but generally observed in the region of higher latitudes, closer to the region of the poles. That is where you will experience this. So it is not aurora, right? Aurora is a title of a name in northern part of the country. It is what is aurora. Or let me write it here. Aurora. It is aurora australis in the southern hemisphere. Aurora australis in the southern hemisphere, and aurora borealis in the northern hemisphere. Okay. Yes, Canada, it will be seen very frequently. In the region of northern part of Europe, it is seen very frequently. In the region of New Zealand, southern Australia, also it is seen very frequently. So those are the areas where you have frequent sighting of auroras. Now we come to the portion of insolation. What do we understand by insolation? So the total amount of solar rays that fall upon a particular region, any particular area, in a given time period, that is what is referred to as insolation. So that solar insolation, when we refer to it, is the incoming solar rays in a given unit area for a given period of time. Now this insolation can have an impact of heating on the planet. This insolation can end up influencing the temperature of any particular region. But it is not going to be the only controlling impact of temperature. Temperature of a particular place is dependent on many different factors. One of these is the amount of solar rays which are received. But there are many other factors. The height is a factor. The winds, they are a factor. The ocean water near them, the temperature of the ocean water near that place, that is a factor of temperature. So temperature is dependent on many factors. Insolation is just one of them. But insolation at various places of the planet Earth, that in itself is not consistent. Why? Owing to the shape of the planet. When we talk about the shape of the planet is spherical, geoid. So if suppose, let's say, I have the solar rays which are coming in consistently. Now these solar rays, observe the angle at which they are hitting the ground. That angle is going to be different. When we are talking about higher latitudes, observe how they are hitting the ground with smaller angles. Isn't it? So different places on the planet, they will experience different amount of solar insolation. That sometimes contributes to temperature change as well. So first of all, let us take a look at the factors which determine the variation in solar insolation or the difference in solar insolation observed in different regions of the world. Why is it? What are the factors which contribute that one area receives more solar energy as compared to the other? Before that, a brief gist about the image that I have attached here so that you get an idea about the climatic aspect that you would have come across the concept. I don't know how many of us read newspapers, but you would have come across the concept when you come across a newspaper headline of a weather report, or let's say any particular news headline about weather report. You would come across something as maximum temperature, something as minimum temperature. Are we aware of that? Maximum and minimum temperature? Good. So, when we say maximum temperature in an area, it basically represents that in the 24-hour period, what is the maximum amount of heating or temperature that is indicated? It is generally measured around 2 to 3 p.m. in the day. When significant amount of heating has already been carried out, it is measured around 2 to 3 p.m. And when we say minimum temperature, that is when the temperature is the lowest. And when is it that the temperature is lowest? When the surface has lost heat continuously. When does the surface lose heat continuously? During night time. So at what time of the night would the surface leave maximum amount of heat? That is later part, 5 a.m. in the morning, when through the night the surface has lost heat. That is where 5 a.m., generally 4 a.m. to 5 a.m., but mostly around 5 a.m. to 6 a.m., that is when you experience the minimum temperature. So next time, when you hear maximum temperature, it indicates the temperature of a region at around 2 p.m. to 3 p.m. and minimum temperature 5 a.m. in the morning. But how do we measure the temperature? You have a different thermometer. The air temperature measurement is done by a unique thermometer. Now, the air thermometer as it is. Now, observe this particular installation here. It appears like a very old kind of the outside air cooler that you see installed in certain houses. But it is not that. It is basically a setup for the measurement of temperature. Here you will find certain perforations all around. That is to allow the air to come in and go out. And inside that casing, you have the thermometer which is suspended in the air. Okay, the thermometer is suspended inside the casing. Now, why so much of hue and cry about measuring the temperature? From our childhood days, we have seen that you take a thermometer, you keep it, let's say, under the armpit, and you get the temperature. You keep it on the ground, you get the temperature. So, why is it that you have so much of hue and cry for measuring air? Can we not simply hold it up like this and get a temperature reading? The answer is no. And here it is basically lifted above the ground. Generally, you will find it is kept at a height of around 1.25 meter above the ground surface. And that is because so that the heating of the ground surface doesn't end up impacting the temperature reading which is being carried out. Okay, that is how thermometers in the case of air temperature is measured. Then here, observe these small cuppings that you have. What is this? This is basically used to measure the wind speed. This is what is referred to as an anemometer. This is what is referred to as an anemometer. It measures the wind speed. So when the wind blows, it ends up rotating significantly. And there we get an idea of the wind speed. This height, it is not it is not as if 1.26 meter will be a disaster. Even if it is 1 meter, fair enough, the job is done. The point is to keep some distance off the ground. Then here, what you observe is your typical rain gauge. To measure the temperature, right? Or measure rather the amount of rainfall which is received. So this is your typical rain gauge. In the case of a rain gauge, the structure is where you have this as a cylindrical jar, and then on top of it, you have a funnel. A funnel is inserted. And that funnel basically leads to the jar. And this jar is going to have markings. In millimeters. That is how we get an idea that here you have that much millimeter of rainfall which has occurred, XYZ millimeter of rainfall which has occurred. That is because of that rain gauge. Okay, so that is what we have as the general in a weather station. These are the instruments that you end up finding in general. Okay, the thermometer, the anemometer, the rain gauge, the barometer. Barometer is used to measure the atmospheric pressure. Okay, now here let us take a look at the factors that end up causing variation in terms of insolation received in different places. So what are those factors? The first factor is angle of inclination of the earth. Earth is tilted on its axis at an angle of 23.5 degrees, which means different areas, owing to the shape of the planet in itself, different areas will receive different amount of solar insolation. We will take a look into that. Then revolution of Earth around the sun. Now, Earth basically moves in an elliptical orbit. Now, when Earth moves in an elliptical orbit, there you will have a position of the planet Earth when it is closest to the sun at a distance of maybe 147 million kilometers. And there's also a position of the Earth when it is farthest away from the sun at at a distance of around 151 to 152 million kilometers, what is aphelion and perihelion. Now, in those areas and in those positions, obviously the amount of solar insolation ends up varying. Then after that, we have the configuration of the land. This basically ends up depicting the direction in which the slope of the land is facing. For example, when we talk about the Himalayan mountain ranges, if ever you have taken a look at the map of India, you would have observed that the Himalayan mountain ranges are to the north. Now they will have a distinct northern face, they will have a distinct southern face also, they will have a face to the north, they will have a face to the south also. So that is something where, depending upon which is facing the sun, it will experience greater solar insolation. And then we have the variation with altitude. So let us take a look at all these factors and let us try to understand that how they end up causing a variation in terms of solar insolation. Anemometer, working of anemometer is very simple. It is when we talk about the anemometer, it has got small semicircular cups. It ends up rotating when the wind moves, and that is where it very strongly, significantly, it indicates you what is the velocity of wind movement. Okay. Vejshri, tomorrow's. Okay, that is not for you, Vejshri. The notification that you have received for Geography Lecture 10 on Saturday, that is for the weekend session. That is not for you. Don't worry. Why thermometer is covered? In order to protect it from, let's say, let's say when the wind is moving, you will have many different interferences, you will have many different dust particles, and if you have a strong wind movement, that can significantly change the temperature readings of the thermometer. That is why it is in a covered casing but with perforations to allow the air passage but not impact the wind movement in that region. Is cloud presence also a factor that causes insolation variation? Not always, in the sense, see, when we talk about factors, those factors stand true for the entirety of the planet. Cloud formation is very variable. So, for a small time duration, it might cause, but in the same region, let's say Delhi, so you will have a lot of solar insolation through the year. Maybe when you have cloud, then insolation might reduce for that moment, but that cannot be considered as a factor. Why auroras happen in the ionosphere itself? That is where you have the heterogeneous distribution of the molecular gases, and that is where you have the maximum impact of the solar rays, and even beyond that. No, there is no class tomorrow, guys. Why are you getting so riled up about it? There is no class about tomorrow. It is for the weekend batch, it is for a different one. Okay. All of a sudden that lecture has on weekend also, I have to revise also, I have current affairs also, how will I manage? All these came immediately. There is no extra class, don't worry. And then when I was saying that we need to catch up, I had all of you suggesting take extra sessions, so that gives me a good insight about it. Okay, so now we talk about the angle of inclination and how it ends up impacting the amount of solar insolation. So when we talk about, let's say, any particular region on the planet surface, here observe any particular region on the planet surface, you will observe that the solar rays, they are not falling at the same angle everywhere. Solar rays, they are making different angles, and in the meanwhile they are covering different distances within the atmosphere itself. More distance that the solar rays cover in the atmosphere, lesser will be the energy which will reach the earth's surface. More distance that they will travel, lesser will the energy be when they reach the earth's surface. This can be understood significantly well as well when we talk about, let's suppose, this being the surface. Let's suppose you hold a torch. Okay. Now this torch will give you light in this region. in this area. And let's say I keep another torch in this area. Okay. And here the light given out will be somewhat like this, isn't it? Now, if we consider this as A, if we consider this as B, both of them will be emitting light. But overall, if you will observe, B will have all its light concentrated in a small area. Why? Because it is making a very high angle, almost perpendicular. When we have sun directly overhead, directly perpendicular, that is when we experience maximum amount of heating, isn't it? So similarly, here also when B, the torch is in position of B, that is when maximum concentration of light will happen in one small area, isn't it? All that light will get concentrated in one small area. Now, here, the amount of energy received will be much more. Also because of the fact that in the case of A, light has to travel a larger distance. In the case of B, it has to travel a very short distance. So when we have the light traveling through very large distance in the atmosphere, much of that energy will be lost or dissipated. And when that insolation travels very little distance, significant amount of heat is retained. So that is why during the time of early morning, at the time of sunrise or at the time of sunset, when the sun is very close to the horizon itself, that is where you will start observing that in those times you don't experience much amount of heat or a higher temperature. And it is only when the sun starts making larger angles, is almost directly overhead, it covers shorter distance, you experience a lot of heating. So it is the angle of inclination which provides for different distances that the solar rays, they will travel in the atmosphere. Larger the distance traveled by the solar rays, lesser will be the impact, or the lesser will be the energy finally reaching the ground surface. Then we have the revolution of the planet, the revolution of planet around the sun. Now, when we talk about the revolution here, we do know that you have different positions, that you have aphelion when the planet is farthest away from the sun at a distance of 152 million kilometers. And then perihelion when it is at a distance of 147 million kilometers. Now, this means at these different areas or at these different positions, the amount or the distance between the sun and the earth, that exhibits a kind of a change. And when that distance exhibits a kind of a change, means what? The insolation will exhibit a kind of a change. So that is why insolation changes when we talk about perihelion, when we talk about aphelion, the amount of insolation changes. But temperature does not indicate a difference in these cases. Temperature does not change drastically with the change in distance here, because temperature is dependent on lot many other factors. Here, this slight change in distance, when we talk about, it might increase or decrease the level of insolation ever so slightly, but it is the tilt. If the northern hemisphere is tilted towards the sun, much amount of heating will be received anyways. So that is why temperature is not only dependent upon this. That is why you will come across a scenario where this will impact the insolation, but not so much the temperature. Then after that, the configuration of land in terms of the directionality of the slope. In which direction is the slope facing? So here again, it is always ideal to imagine and take a look at the various different places, various different places. here. Let's suppose this is the planet. Now, if you have a mountain in this region, it will have a north face. It will also have a south face, right? Now, if the position of the sun is here, now, which of these faces do you think will receive direct rays of the sun and greater direct rays of the sun? North face or south face? What do you think? Very good. It will be the south face. Why? Look at it. Very simple. The direct rays of the sun, they will impact the south face quite significantly. Now, the converse is also going to be true in that case. The converse is also going to be true. For example, let's suppose you have a mountain range in this area. It will also have a north face and it will also have a south face. So in that case, what do you think? Which face will receive greater insolation of the sun? North face always, right? So the position of the sun, depending upon the position of the sun and depending upon the region that we are talking about, when you have a particular region having a north face and a south face, that is generally observed in places where you have the slopes. So where the slope is, let's say, directed towards the sun directly, there you will have a greater insolation. Now, when you think about the Himalayas, when you think about the Alps, I hope we have a rough idea about their location. Now, in the case of Himalayas and Alps, which face will receive more direct rays of the sun? The north face of the Himalayas or the south face of the Himalayas? What do you think? Very good. Beautiful. So it is going to be the southern face. Southern face of the Himalayan mountains, southern face of the Alpine mountains, they will receive direct rays of the sun at a greater proportion. They will receive higher insolation. As a consequence of that, that is why you will find that the Alpine mountain ranges and even in the Himalayan ranges, majority of the habitations and the settlements and the various different areas that you have where people inhabit, all of these areas majorly are concentrated on the south face of these mountains because greater insolation of the sun makes the conditions much more livable, makes the conditions much more tolerable. North face, you will experience extremities because direct rays of the sun are not received. So that is basically the aspect. Why only southern face of mountains? Okay, Anshu and Palak, think about it carefully. Let's forget the northern hemisphere for a bit. Okay, let's think about the southern hemisphere. Now, here in this southern hemisphere, you have a mountain in that position. It has got a north face and has got a south face. By the way, it is not necessary that all the mountains will have a north and a south face. If you take the example of, let's say, the Andes, it will not have a north and a south face. So which mountain will have a north and a south face? So all those which are running east to west, all those mountain ranges which are moving from east to west. For example, Himalayas, they extend from northwest, they move to northeast. It will have a distinct north and a south face. When we talk about, let's say, the Alps, they again move from east to west. Rockies, Andes, Ural, they move basically north to south. So there you won't have north or south face. Okay. So here, if I ask you, the question that in this mountain, which will experience greater sunlight of the sun or greater light of the sun, greater solar insolation, what do you think? Will it be the north face which will receive, or will it be the south face which will receive greater amount of insolation? I want two of you, Palak and Anshu. Think about it and get me back with an answer. Yes, Preeti, more often than not. This is the hemisphere that we are talking about. It is going to be the north face, right? So north face is going to receive greater amount of solar insolation. Why? Because when we talk about the north face, here it is directly facing the solar rays. That is why. So if you think about this as the equator, let's say in the southern hemisphere, if you have a mountain, and let's assume that the sun is at equator at that point of time, so here you will experience that the north facing slope will experience direct rays of the sun. South facing slope, in the case of northern hemisphere, they will end up facing direct rays of the sun or greater amount of insolation. Is that understood? Okay, or is there any doubt? Is it so that southern phase of mountains in northern hemisphere will receive direct rays of sun? Yes, that is so. But equator has thick atmosphere, then how? Equator has thick atmosphere, then how energy reached more? See, the thickness is not referred to. Please don't mistake thickness with density. Most of you guys have been mistaking thickness with density ever since the time of continental crust and oceanic crust. Anything which is thick doesn't mean it is going to be dense enough. So troposphere in the region of atmosphere is thick enough, but the air is less dense. In the region of the poles, the air is much greater dense. So that is why, and the region of equator receives greater energy because of the position, not because of the air above it. It is in that area where maximum solar insolation will be reaching at a perpendicular angle. That is why, and for the majority of the part of the year, that is why equator is very heated. Okay. I'm a little bit confused about thawing permafrost in Arctic region, even in northern hemisphere. They are mainly composed of landmass. Yes, the permafrost regions are surrounded by they are the landmass surrounding the region of Arctic. What is the confusion in that? Okay. Yes, insulation is relevant and important for your exams. Is this land configuration also available for the whole planet? Yes, it is available for the whole planet. In the entire regional aspect of the planet, you will come across this. Then we come to the factor of altitude. That how with the change in altitude, the insolation ends up changing. So for example, let's suppose we consider different places indicating different heights. Let's consider a particular region at a height of 4 kilometers as compared to one which is at sea level. So here, if we assume this as the top of atmosphere, now when the solar rays, they are reaching the planet surface, in order to reach the sea level, they have to cover much larger distance through the atmosphere. In order to reach a higher altitude, they don't have to cover that great a distance. They are able to reach quite significantly. So that is why amount of insolation is very high in the higher altitude. Does not mean temperature is high. The amount of insolation is going to be very, very high at a greater altitude. So that basically means that the intensity of the solar rays will decrease as you come to the sea level. That is why when you go mountaineering, when you go hiking, or not hiking, but mountaineering beyond a particular height, you get impacted by sunburns. Your skin starts to burn off. That is why you will find the mountaineers, they have all the protective coating. They even have the glares, the sunglasses, to protect them from the solar glare. So that is basically the aspect of altitude and the variation in on insolation as the factor of altitude. Okay. If insulation is higher, why temperature is not higher? Because we have already talked about it, that temperature has many contributing factors. Many factors associate with the factor of change in temperature. We'll come to it very next, and after the break we will take that up, that particular portion where we talk about the factors which influence the temperature of a place. So you will find out that it is not something which is only dependent on insolation. Insolation is something different. And by the way, I've seen many of you mentioning this as insulation. Insulation is an absolutely wrong thing, wrong term to be used in this aspect. Insulation is what is present in the wirings. Insulation is what is present in terms of insulators, heat and current insulators. This is not insulation. This is insulation. There is an O here. Okay, so please stop referring to it as solar insulation. Okay, don't do that because you'll get into a habit of doing that. Okay. Preeti, Rocky Mountains also spread from north to south means they will also not experience change in insolation. Look at the shape of the Rockies once. It is very interesting. Some portions they do. So that is where we take a break and we come back after 10 minutes. Okay. And then we will continue. Then why in valley region formation of temperature inversion like situation? Let us come to temperature inversion first of all. We'll talk about it why temperature inversion takes place. That is given rise to with the help of the mountain winds. Mountain winds are responsible for the temperature inversion taking place in the valley. So it is a very different concept altogether. Again, I will repeat, why is it that the temperature or rather the insolation varies at different places with altitude is because if you consider a place at an altitude, a place at a particular height, if you just consider the distance traveled by the solar rays in the atmosphere to reach that height, and you compare it with the solar rays and the distance traveled by the solar rays to reach the level of the sea or the main sea level, that is where you will find that this is a longer distance, right? So greater the distance traveled by the solar rays in terms of the atmospheric region, greater will be the loss of energy. That is why energy received at the sea level will be much lower as compared to the energy received at an altitude. That is why the amount of insolation is much higher at a particular height as compared to the sea level. So closer to the ground, more atmospheric particles come in the path of the solar rays. That is where the intensity of the solar rays, they get impacted. So I hope that is clear now. Okay. Deepak and Anjali, you had a question about it. So I hope that is clear. No, Deepika, insolation is not equal to temperature. Insolation and temperature, they are very different factors. Okay. So after this, we come to the few of the other basic concepts of heating and cooling. So we start with the portion of albedo. Albedo basically gives us an idea about the amount of solar rays reflected from any particular surface. That is what is referred to as an albedo. So it gives us an idea about the portion of solar energy reflected from the surface of Earth back into space. It has a variation. It has a variation with types of surface. As different surfaces will reflect different amount of solar rays. For example, if you take this case of A covered with ice, and if you take this B, a landscape which is covered in marshes and grasses, out of these two, just by visual appearance, where do you think greater amount of solar rays will be reflected and where do you think less solar rays will be reflected? What do you think? A, easy. So in the region of A, you will find greater reflection of solar rays. In the region of B, lesser reflection of solar rays. So if less solar rays are reflected, means where does the rest of the solar rays go? It is absorbed by the surface. Let us take a look at that. So this albedo, it varies between 0 to 1. Varies between 0 to 1. 0 indicating no reflection, maximum absorption of the solar rays. Maximum and complete absorption of the solar rays. Whereas if any material, let's say, has an albedo of 1, it indicates no absorption and complete reflection. So it ends up varying between 0 to 1. So if I say the albedo of ice, in particular, let's assume the albedo of ice. So if the albedo of ice is 0.85, that means what? That means it ends up reflecting, if the albedo is 0.85, let's suppose. That means 85% of solar rays are reflected and 15% is absorbed. 15% of these solar rays, they are absorbed. 85% of the solar rays, they are basically reflected back. So, for example, when we consider any type of surface, understand this. Let's consider different surfaces. So, if in the first case, let's say the albedo is 0.7. In the second case, let's assume the albedo is 0.2. So in the first case, 70% of the received solar rays, they are reflected back. That means 30% is absorbed. In the second case, albedo is 0.2. That means 20% is reflected back. 80% of these solar rays, they undergo absorption. Okay? So if I mark it as 1, if I mark it as 2. So here, which of these surfaces will end up indicating a higher temperature? A, or the first case, or the second case? Which will indicate a higher temperature? Very good. It is the second case, right? Or the second sample. Why? Because here 80% of the solar rays, they are absorbed, and here only 30% is absorbed. So if by this, can we have a conclusion that if the albedo is less, there is greater heat absorbed and there is a higher temperature indicated? So we can have the conclusion, if the albedo is less, means more absorption and resultantly a higher temperature. Okay, so resultantly a higher temperature and there is more absorption. So that is why, if during afternoon times, if ever you step outside your house during this particular season, this particular climate, when it is very, very hot, if you take a look at the road, the black tarred roads that we have, now, if you happen to touch the surface of the road around 2:30 p.m., 3 p.m., it will be very, very hot. But let's suppose your house is painted white from outside and you touch the surface of that house, you will find that it is cooler, because owing to the white color, it ends up reflecting significant amount of solar rays, and the road surfaces being darker in appearance, they will absorb greater amount of solar rays. So that is why it is always advisable, even you would have read it in basic science in your school days, it is always advisable that during the summer season, during the summer months, one should always end up wearing light colored clothes, because it absorbs less heat, it reflects more. So as a result of that, you end up remaining cooler. And during the winter months, that is why it is always advisable to wear dark colored clothes, because it will absorb and retain greater amount of heat. So that is why you have the variation in temperature depending on the type of surface. If the surface is bright colored, for example, we have the snow and ice covered areas, majority of the solar rays, they are reflected back. Now that is one other reason why You will find that the mountaineers, the expeditioners, they will never climb the mountain, especially the snow-covered peaks. They will never climb it without a protective eyeglass or a kind of an eye shade, because the amount of solar rays being reflected from snow and ice is so great that it can damage the eyes as well. So that is why you will find them wearing those protective goggles, because when they are climbing over the ice, a lot of that solar rays gets reflected back. Okay. In some regions, when the sun's rays are coming and the same time rain is happening, then what will be the role of albedo? See, please understand, it is not as if albedo will be the chief factor for temperature determination. It is not as if insolation will be the chief factor for temperature uh, determination. It is dependent and varied on a multitude of factors. Okay. Albedo just gives you, for example, it will help us understand the concepts when we talk about why Tibetan highlands and the Tibetan plateau, when we talk about Indian monsoon, that Tibetan plateau and Tibetan highlands, they reinforce the Indian monsoon. They end up bringing greater rainfall in the Indian monsoon, because the Tibetan highland gets heated more significantly than the surroundings. And that is because the Tibetan plateau is consisted of dark colored rocks which have been created long time before. So it is in those areas that you come across the factors of albedo. Even when we talk about the urban areas, in the urban areas, you will find a lot of these concrete buildings, which will absorb a lot more, reflect very less. That is why in urban areas, you experience sudden high temperature. Okay. What you are talking about, that there is rainfall and the sunlight at the same time, I hope you will agree, when both of these incidents happen, the intensity of sunlight reduces. Sunlight is not powerful anymore, right? So obviously the factor of absorption and reflectiveness doesn't come into the picture. So that is the factor of albedo. Now, how is it that albedo and the factor of albedo induces an accelerated rate of polar melting, particularly in the region of Arctic? Not in the region of Antarctica, but in the region of Arctic. Why Arctic? Because Arctic is an area of ice sheet and ice mass above water body, whereas Antarctica is ice sheet and ice masses which is present over a continent. I hope we are aware that when we talk about Arctic, there is no land underneath it. So if the ice melts, water is exposed, and water and ice will have very different levels of albedo. Even in fact, when we talk about different types of ice, thicker ice, thinner ice, and so on, they will also end up reflecting varying amounts of lights. For example, if I ask you, let's suppose you consider this ice sheet, and let's consider, name this as 1. Let's consider a thinner ice here, 2. Out of 1 and 2, where do you think there will be greater amount of reflection which will happen? Out of 1 and 2, where greater reflection will happen? Obviously, in the case of 1, very good, very nice. More reflection will happen in 1. Why? Because you have thicker layer of ice, very, very white and bright in color. When you have ice which thins out, you will observe that the thinner ice that starts becoming transparent. And when the ice becomes transparent, its reflective ability that reduces, it starts absorbing more heat. So let us try to understand that how is it that the property of albedo induces increased rate of melting in the region of Arctic. So first of all, if we take a look at the region or the basic reason why the Arctic ice is melting, so that is because of global warming. Okay, global warming. And observe this chronology carefully. Global warming induces melting of ice. Melting of ice. Or even thinning of ice, anything. Now, melting of ice, when it will happen, that means water gets exposed. water gets exposed. Okay. So melting of ice means water gets exposed. Now the water that you will find here, its albedo will be very different from the albedo that you find in the case of ice. Water's albedo is much lower. Water's albedo is roughly around 0.2. So it will reflect only 20%, absorb almost 80%. So when water gets exposed, means what? Will absorb more heat. More heat. When that water and the surrounding region will start absorbing more heat, that means temperature will increase. Temperature increases. As the temperature increases, what will happen as a consequence of this? It will further fuel greater melting of ice. And it is a kind of a feedback loop. It is kind of a feedback cycle. So that is why once that melting of ice has been initiated due to climate change and global warming, that will continue to bring about cascading impacts, and that will continue to trigger much more heating in that area. So that is why in the region of the Arctic in particular, melting has been accelerated with the exposure of more areas of water. Okay, that is why in the region of Arctic, hence in Arctic region, melting has accelerated due to water getting exposed. Okay, when water is exposed, that is when you will have a significant acceleration of melting. Now, out of ice and snow, ice will have a greater albedo. So we need to be concerned if ice melts in Arctic as it would rise sea level, then ice melting in Antarctica as the ice on the continent, it would not lead to the rise in water level. See, rise in water level is caused because of multiple different factors. One of the major causes why water level rises is actually thermal expansion and not melting of ice and glacier. So in the region of Antarctica, why it is not prominently found is that in the region of Antarctica, above the land, you have 2 to 3 kilometer thick deposit of ice. Whereas in the region of the Arctic, you will find many areas where the water is exposed easily. That is not the case that you find in the region of Antarctica. However, with global warming, the coastlines of Antarctica, they end up remaining ice free for a larger part of the year. And when they are ice free, they will start absorbing more heat. That is why you will find that in the coastal areas, there is increased rate of melting in Antarctica, but in the region of Arctic, the entire portion simply ends up melting it out. Okay. Sir, you said that white color paint maximum absorb, no, maximum reflected. White colored paint is maximum, is going to reflect maximum, absorb minimum. Then why does white ice not maximum absorb? Because I never told that. I always told that white color will always reflect maximum. Black will absorb maximum. Okay, please don't get confused. But don't you think with continuous reflection leads to melting of ice? No. Why will it? If there is ice, there has to be a low temperature which will support that ice. That is why there is ice in that region. You won't find ice covered areas in Hyderabad or Bangalore. You find it in the region of the higher latitudes or high altitudes. Why? Because the temperature is low enough. So that is why you find that extreme low temperatures formation of ice. If it absorbs only around 20% or 10% of the solar rays, the temperature will remain low enough. If it starts absorbing more, that is when melting happens. Cascading basically, okay, it is an English terminology where when we talk about cascading, one particular impact or one particular event which will have a follow-on impact in other areas also. That is what is cascading. Okay. Yes, melting of ice will lead to an increase in water level. If glacier reflects most of the direct sunlight, means the glacier doesn't melt due to direct sunlight. Glacier melts because of global warming, and glacier melts as it comes after a particular height. When it comes below the level of the snow line, that is when the temperature increases, and that is where you observe the glacier melt. Okay. After water getting exposed, why will water absorb more heat? Because water has got lower albedo. Water will reflect lesser as compared to ice, will absorb more. So that is why ice has got one of the highest reflective coefficients. It has got the highest reflective property. That is why ice will reflect maximum. Can we say global warming is analogy to cascading? Absolutely not. Why no albedo effect in Antarctica? In Antarctica also you will experience that albedo effect. Okay, Juno mission of NASA. Okay, you are talking about a mains question which was asked. That will be covered in Science and Tech. Etisha, it will be covered in Science and Tech, that how Juno mission helps us understand the evolution of planet Earth. It was asked in mains 2017, if I'm not mistaken. It basically talks about the Juno mission explores the Jupiter. It moves around the Jupiter. It explores Jupiter significantly and the inner surfaces of Jupiter. And it also tells us about the factors of rotation and how earliest collisions would have happened. Okay. What are the conditions due to which we can understand about albedo of different things? As in, do you guys need a list? Is that what you are seeking? The list of different surfaces with different albedo? Is that what you are seeking, or is it something else? Ice less absorbs sunlight, then less melting of ice. Ice less absorbs sunlight than less melting of ice to make water. Guys, at least put your questions in a way that it makes sense. It might make sense to you while you are typing, but it makes no sense while reading it. So frame your question accordingly. Cloud on top of it, the albedo will be very high, Fayaz. Okay, Pratibha, you will get that list in the additional reading materials. That list you will find there. Why different surfaces have different albedo? Will all the surfaces be able to reflect the solar rays in the same manner? If, let's say, I have this black colored clothing, will it absorb the same amount of light as, let's suppose, this metallic surface? Always, obviously not. The impact of the surface, the coloration will be very, very different for all of this. That is why different surfaces have different albedo. Can we say albedo and polar melting are the same? Absolutely not. Please don't get that idea ever. Albedo is basically the reflective coefficient of a surface. Even the rivers will have an albedo. Overall, the planet Earth has an albedo of 0.2. This particular surface will also have an albedo. The walls in your house will have an albedo. Albedo is surface dependent. How can we relate it to polar melting? Where does that doubt come from? Process of desertification does not have climate boundaries. Is it from geomorphology? No, it is from climatology. Okay. So now we come to the basic concept of heating of land and water. How is it that land and water, they react when they are exposed to significant amount of heating by the solar rays? So here, let us consider a landmass. and a nearby water body. Okay. Now, solar rays are received on the land. And whenever we talk about water body here, we are talking about larger seas and oceans. We're not talking about small ponds and lakes. And solar energy will also be received here. Now, when the solar energy is received on the land, do you think it will penetrate the land surface significantly, or do you think it will be restricted to the top of the land surface? Generally, as you would have observed, it is restricted to the top of the land surface. So over the land areas, the solar energy is restricted to around top 2 to 3 centimeters or top 3 to 5 inches at max, not more than that. That is the only region where the solar energy is able to reach. Whereas over the water body, when the solar energy reaches, there, what do you think? Is it restricted to a small area or is it going to spread? So water is almost transparent, so it will spread. It will spread significantly. So when it comes to gaining the heat, indicating a temperature change, where do you think heat will be gained much more quickly? In a region where the heat is restricted to the top surface, or in a region where the heat is thoroughly distributed? Obviously, where the heat is restricted, right? Where the heat is restricted, that is where significant amount of heating will be observed. So, the basics. Solar energy on the land. Land is restricted to the top 3 to 5 inches. And solar energy on water gets distributed in two different layers. So that brings us to a set of conclusions. The first conclusion that we'll make out of it: heating of land is going to be much faster as compared to heating of water. Heating of land is much faster as compared to heating of water. Now, during night time, let's suppose throughout the day, the land has gotten heated and water also somehow has gained temperature due to solar exposure throughout the day. Now, during night time, you don't have any heat which is gained. Heat is lost by terrestrial radiation. Now, in one region, that is over the region of the land, all that heat is restricted to the top 3 to 5 inches. In the case of water, the entire water body exhibits a kind of a temperature. So, where do you think the loss of heat will be faster? Over the land area or over the water body? Where do you think? Good. It will be over the land area, because all that heat is restricted to a small thin layer, whereas for the water body to lose temperature, it has to lose temperature from all the various different depths, and that is when it will indicate a temperature change. So that is why loss of heat is much faster over land as compared to water. Again, I will repeat. So basically, when we have the land, in the land area, it will be heated significantly. Why? Because on that land area, the entirety of that solar energy will be restricted to the top few centimeters and top few inches only. That is where the entire solar energy will be concentrating upon. So it will get heated up very quickly. Whereas over the water body, that solar energy will get distributed. It will get distributed at the various depths of the water. So for that water to exhibit 1 degree Celsius temperature rise, it will take a lot more time. That is why heating of land is much faster. Now in the land, all that heat is restricted to that particular thin layer itself on the surface. So it will manage to lose heat very quickly. Whereas over water, you will observe that the heat is significantly distributed. So for the water body to lose heat, it will take a lot more amount of time. Now that gives us to the applications of it. So during daytime, we have the gain of heat. So which will be warmer? Land becomes hotter much quickly. So always during daytime, you will find land is much hotter. Water is cooler. Now, during night, we have the loss of heat. During night, we experience a loss of heat. Now, we know that land loses heat much quicker. So, which will be colder during the night? Perfect. So, that is why during night, land is colder and water is warmer. That also brings us to the other conclusions, the seasonal conclusions. During summer, you have a prolonged phase of 4 to 5 months when the heat is significantly gained. So that is why during summer season, you will come across a scenario where land is much hotter. Water is cooler. And during winters, when we talk about the winter season, so what happens? During winter season, there is a loss of heat, a continuous loss of heat, isn't it? So land loses heat very quickly. So that is why during winters, you will always find land is colder, water is warmer. Okay, so this is always at the same latitude. At the same latitude when we are comparing. Okay. Now, this basic is going to help us significantly moving ahead when we talk about not only temperature distribution, isotherms, when we talk about movement of winds, causation of rainfall, this factor of heating and cooling is going to come to our rescue. So rather than learning it up, just whenever that portion comes, or whenever you are faced with a problem that you have to find out which is hotter, which is colder, always go to the basics, think about it, that which will gain heat quickly, which will lose heat quickly. Always water will lose heat slowly, land will lose heat quickly, and land will gain heat quickly and lose heat quickly as well. Okay. Now, then after that, we come to another concept, that is what is referred to as urban heat island. So this is something that you would also have experienced in your day-to-day life. Now, you would have experienced that when you enter an urban area from a suburb or a rural landscape, when you enter an urban area, you experience a sudden rise in temperature in that urban landscape. Whereas in the nearby vicinity, you observe that the temperature, this is, let's say, the graph indicating temperature. So in the urban area, suddenly you will experience an increase in temperature. And that is what is referred to as urban heat island. Why urban heat island? Because it is that heated portion surrounded by comparatively cooler areas. Hence the analogy of an island. So this urban heat island is that part of an urban or a metropolitan area that is marked by remarkably high temperature as compared to its rural counterpart due to excessive human activity, due to excessive construction, human activities, etc. That is why in this region you experience a higher temperature. Now here, when we talk about it, why is it that the urban areas exhibit that high temperature? Why is it that we experience that as we go into the suburbs, the temperature is much more tolerable? So there are various different reasons and factors for this. So when we talk about the reasons, first of all, in the urban areas, you have a lot of construction, lot of roads, asphalt, tarred roofs, etc. for waterproofing purposes. So a lot of these dark surfaces are present. So due to darker surfaces, that means lower albedo. That means greater reflect absorption. That means what? Higher temperature. Higher temperature. Okay. Now, when we talk about other factors, so in the urban area, the central business district of an urban area, you will find a lot of the clustered buildings, buildings in very close quarters. Now, these buildings, they don't allow the passage of winds in that region. They won't allow the free and frequent movement of wind. And also, the loss of heat will actually be inhibited. So heat is trapped between these areas. If the wind blows, you will suddenly experience that it becomes much more cooler, it becomes much more comfortable. But if the wind is not in existence, the hotness of it or the temperature becomes much more oppressive. So less movement of winds leading to lesser heat dissipation, which means higher temperature. Higher temperature. Then, lack of green cover leading to lesser cooling. Now, when we have the green cover in any particular area, means the trees, the forests, anything. First of all, it provides direct cooling of the land by providing shade, right? So if you don't have green cover, means there's a greater exposure of land to direct sunlight, means greater temperature will be experienced. And secondly, all the trees, they end up losing water continuously by the process of what is referred to as transpiration, right? Where the trees, through the leaves and the pores in the leaves, they continue to lose water in the atmosphere through the process of transpiration. So if whenever there is transpiration or whenever there is any kind of evaporation, there is an associated cooling with it. So that is why when we talk about lack of green cover leading to lesser cooling, that also means lack of areas under shade. Okay, lack of areas under shade and also lack of transpiration leading to lesser cooling. Okay, that is what you experience. Okay, guys, we'll take a 3 to 4 minutes break here. There is some technical issue. So wait, hold on for 3 to 4 minutes and we'll be back in 3 to 4 minutes. Okay, just wait for 3 to 4 minutes here. Okay. Okay, just confirm the availability of audio once, if the audio is clear and available. Thank you. So, lesser dissipation of heat means that heat is taken away. That is what is referred to as dissipation of heat. Okay, so here, that is how lack of green cover brings about a lesser amount of cooling. Then we also have a significant lack of open soil regions. Now, in urban landscape, first of all, you don't come across a green area. And more particularly so, in these urban landscapes, you will not come across an area which has open green cover and presence of soil, let's say a grassland of sorts. Now, what is the role played by them? So, in open soil areas, when you receive rainfall in a region, let's suppose, excuse me, when you receive rainfall in a region, now as a result of this rainfall, what happens is there is availability of moisture here. That moisture slowly and steadily over a period of a few days, they will evaporate. Now, whenever evaporation happens, there is an associated cooling of the surface, right? For example, whenever you start perspiring, whenever there's perspiration or sweat rolling down, as that sweat or perspiration evaporates, your skin becomes cooler, isn't it? So that is why evaporation is always associated with cooling. So lack of open soil regions means that those areas which would receive rainfall and would cool the region by evaporation after a point of time, that process is inhibited. Because in urban landscape, what do you have? Immediately all that water is directed into the storm water drains. Immediately it is taken through manholes and sewer pipes and into the drainage network. Now, that does not mean that you should not have sewer networks in the region of the urban landscape. You should not have drains. No, it only means that if you have more open spaces under vegetation, there will be significant amount of cooling because evaporation will also end up happening. Okay. So here, lack of open soil regions, when we talk about, this is impacts the cooling after rains due to evaporation. And here, ideally, one should not have barren soil. That is never going to help. Barren soil increases the rate of heating. One should have green spaces. That is something which should be present. Now, in urban landscape, because of greater population and higher population density, we also have greater greenhouse gas emission. That is something which you also experience. So greater amount of greenhouse gas emission means what? Greater retention of heat because of greenhouse effect. So that means greater retention of heat, greater retention of heat. And when we have greater retention of heat means higher temperature. Isn't it? Then after that, you have greater heating due to electrical and cooling devices also. In the urban landscape, in urban areas, you will always come across a scenario where there is a greater utility or greater application of electrical devices. For example, in the buildings, in office spaces, you will find that the tube lights and all the electrical or air conditioners, they are switched on throughout the day. Now, whenever you switch on an air conditioner, I hope we understand, while it cools down the air inside the room, it causes warming outside the room. So, greater utility of these particular appliances means greater heating of the air surrounding. So, all these factors are contributing to the urban landscape, indicating a higher level of temperature as compared to the surrounding areas. So, what should be the solution? The solution should be green buildings. Now, by green buildings, it doesn't mean that paint the building green or have plants on the building. No. When we say green buildings, it basically refers to those efficient, energy efficient buildings which have natural aeration, natural movement of air, so that you don't need that great application of air conditioners. You have natural light which comes in, so that the usage of electrical appliances that is reduced. And for that, You have many nowadays, the entire concept of architecture has changed into natural architecture, where the designing of large office spaces and office buildings, that takes a kind of a leaf out of the book of the ants. When the ants, they make ant hills in nature, you would observe, I'm sure you would have observed ant hills out in the wild, or even on the side of the roads. Many of the times you observe that ant hill. Now that ant hill has got close to around hundreds and thousands of pores through them. And despite the high temperature outside, it has been observed that the temperature inside the ant hill is significantly cooler. Why is that? Because they end up forming those multiple channels and pathways in that ant hill, which will allow the passage of air, which cools it down, which brings the air in a kind of a motion and allows the movement of it, even if there is no wind. So that is where architectural concepts and designs are being now encouraged, and inspiration is being taken from them. Then you should also have the conditions of more availability of open spaces, green parks, etc., in various urban landscape. That provides a significant level of cooling associated with it as well. So these are the solutions and the problem of the aspect of urban heat island. Okay. Shelly, the vehicle heat, industrial machinery, all of that you can include in the greenhouse gas emission itself. Okay. Right? I hope that is understood. Which reason, Rahul? So I hope this is a concept which is now understood. In the process of day and night, heating and cooling of land and water, the concept of albedo works always. Any surface, let's suppose this watch, wristwatch that I have, it will have a different albedo than the skin of my hand. That will have a different albedo than, let's say, the color of my cloth. That will have a different albedo than, let's say, where you are sitting and the color of your cloth maybe. So all the surfaces, they will have a difference of in terms of albedo. Lack of soil. Okay, lack of soil basically here refers to open areas of vegetation. So if we don't have enough areas, open areas under vegetation, what ends up happening is that, see, after rainfall, these open areas of vegetation, they will have lot of moisture which is absorbed. So over the next period of couple of days, that moisture will be consistently lost due to evaporation. Whenever there is evaporation, there is going to be an associated cooling of the land surface. So if you don't have these open areas, what do you have? Lack of this cooling. In the urban landscape, immediately when there is rainfall, all that water is immediately drained through storm water and rainwater drains. So you don't have significant amount of evaporation causing that cooling impact on the surface. Okay. Heating due to electrical equipments and cooling devices. Here, cooling devices refers to the air conditioners. The air conditioners that you utilize. They will, so in urban landscape, you have increased concentration of all of this. They will warm up the air and atmosphere outside. It is a huge population, Abhishek, which is leading to all of this. But yes, you can also write that. And CFC is also a gas responsible for greenhouse effect. Yes, but CFCs are now banned. Now HFCs are the gases in fashion, which are causing that increased amount of warming, so to say. So now we come to the aspect of temperature distribution. How is it that temperature is different in different parts of the planet, and why is it so? So we take a look at the factors of it. So when we take a look at the various factors influencing temperature, the first factor is the latitude of the place, the latitudinal position of the place. Now, here, the impact is very simple. Now, we have already seen at the portion of studying about insolation that different areas end up receiving the solar rays at different angles. Right? Different areas, they receive solar rays at different angles. So if we have let's suppose, an area receiving the solar rays at this angle compared to an area which receives solar rays at a slanting angle. Obviously, where you receive direct rays, vertical rays, there will be significant amount of heating, high heating. That is why at lower latitudes, where because of the location of and the position of and the shape of the earth itself, at lower latitudes you experience greater amount of solar insolation at a high angle which is made, that is at direct angles, that is direct rays of the sun. Now in those cases, always the temperature indicated will be very, very high. Okay, so generally across the lower latitudes you will end up finding very high amount of temperature in general. As we move to higher latitude, the tilt of the solar rays that becomes very apparent and significant, and that is where you don't have any amount or significant amount of heating is not caused. That is why in general, as you move away from the equatorial area to the polar area, as you tend to move away, you experience lower temperatures. Temperatures are highest in the lower latitude. It is significantly lowest in the higher latitudes. Then the other factor, altitude of the place. Now, altitude refers to height. So we know that with the increase in height, the temperature reduces. Okay, so it becomes colder as you start moving up at a rate of close to around 6.5 degrees Celsius per kilometer. But we had seen just now that at an altitude, the amount of solar insolation is high. We have seen that, isn't it? That solar insolation is higher at a altitude, right? So why is it that despite the solar insolation being higher at a particular altitude, the temperature is low? Let us understand that. So here, let's suppose you have the condition of a mountain. Yes, Sachin, very good. So here, let's suppose the altitude is 6 kilometers. And this is at mean sea level. Now, during the day, there has been heating which has occurred. Significant heating has occurred during the day, so the temperature has risen up. During the night, that temperature will be lost by the surface. Now, when we talk about the air density, we do know that air density is very high, closest to the sea level. So, high air density in this region. We will come across very high air density in this area. And in this area, we have very low air density. Very low air density in this area. So basically, during night time, when you have to take a case of loss of heat, that is what happens during night time. So heat will be lost from both the regions. Heat will be lost from here also. Heat will be lost from here also. But above the mountain, the density of air is very, very less. So when the density of air is less, its capability to retain heat will also be less. That means it will continue to lose heat very quickly. Whereas here, as the density is significantly greater of the air immediately above the ground, the density is higher. So in that case, what will happen? There will be greater retention of heat, isn't it? So that means that loss of heat will be limited. That means the temperature will be different. That is why you will observe that there is a greater retention of heat at the lower levels closer to the sea level as compared to the top of the mountain. It is one of the reasons why the top of the mountains, they are colder during the night, significantly colder during the night as compared to the region at a lower elevation. And during the daytime, when the sunlight is coming, Reflection of sunlight happens if the region is covered in snow. Otherwise, if let's say we are talking about a hill station which is not covered in snow, for example, Darjeeling, for example, Ooty, if we are talking about these areas which are not covered in snow, there, that loss of heat factor and the normal lapse rate, they are instrumental in maintaining the low temperature. That is why temperature is low at an altitude despite the high insolation, and temperature is high at lower level despite the low level of insolation. Okay, I hope that is understood. Now, a couple of other factors. The distance of a place from the sea. Now, you will always come across a scenario where coastal areas experience more moderate temperatures. Coastal areas experience more moderate temperatures. Moderate temperature. Whereas inland areas, the areas which are away from coastline, they will always experience extremities of temperature. Areas away from coastline experience extremities of temperature. Why is that? Let us understand the reason. So, here, first of all, when we talk about a coastal landscape, a coastal area, now there, coastal area means you will have a sea or an ocean nearby. Now, wherever you have such a large water body, there will be significant amount of evaporation also. That means a lot of vapor will be present in the air, isn't it? And vapor, when you have water vapor, vapor tends to retain heat. It doesn't allow the loss of heat very quickly. So wherever you have greater amount of vapor or moisture in the air, that means there will be consistency of heat because the vapor will be able to retain heat, isn't it? So first factor is greater moisture presence in coastal areas ensures the retention of heat and maintenance of temperature. But a larger factor involved, a greater and a more major factor involved, is the fact that the thermal heating capacity of land and thermal heating capacity of water, that is different. Land gets heated at a different rate, water gets heated at a different rate. This induces a kind of a consistent wind motion in the region of the coastline due to that thermal difference that brings about in existence the winds, what we refer to as land breeze and sea breeze, which we'll study in much greater detail in the next module. So these land breeze and sea breeze, which frequently end up blowing every day during daytime and nighttime, that also provides a level of moderation of temperature. Whereas in, let's say, an inland area, an area which is present in the interior, let's suppose, you don't have that frequent movement of the winds, due to which heat is allowed to build up, and conditions during the winter season, they are allowed to cool down significantly because you don't have that regular exchange of wind. So that is due to thermal difference. Thermal difference. There is what? regular movement of sea breeze and land breeze. Regular movement of land and sea breeze. And that ends up moderating the temperature of that area. Doesn't allow the heat to build up, doesn't allow the temperature to get very cold. That is why even at the same latitude, you will experience that the areas across the coastline, they have a moderate temperature, whereas areas in the interior, they have a much higher temperature. Okay. For example, take the case of even higher latitudes. For example, take the case of Greenland. Coastal regions of Greenland, they get to be ice free for significant some part of the year because they are closer to the coastline. Whereas the interior regions of Greenland, significantly, they remain frozen for most of the year or throughout the year, because there you don't have the influence of this moderating temperature. So that is where distance from the sea is a controlling factor. And then we have the prevailing winds. Prevailing means the winds which are in existence, the existent winds. So in any particular area, we can have the influence of winds impacting the temperature by the process which we refer to as advection. We had studied advection yesterday. So by the process of advection, advection influences temperature. Influences temperature. That means warm advection will lead to higher temperature. Cold advection will lead to lower temperature. Okay. Point of thermal difference is that the temperature of land and water, they are not going to be the same in the coastal area. Land is going to exhibit a different temperature, water is going to exhibit a different temperature. That induces a wind movement in that local area. And we will study more about land and sea breeze in the next module. We will understand why that blows, when that comes into existence. We'll come to all of that. But because of that thermal difference in the coastal area, you will experience that the wind always is in motion, either from sea to land or from land to sea. So that brings about the mixing of air and doesn't allow the temperature to go to an extremity. When the Greenland is frozen, then why we call it, okay. So this is a kind of a different question. I thought it is a kind of a geographical question. Okay, fair enough. Now, what is thermal difference? Difference in temperature. How can equator receive more insolation because the earth is tilted? In general, the lower latitudes receive more insolation. The temperature is different. Temperature is never going to be highest at equator, if I tell you that. But here we don't understand the concept of high pressure and low pressure, at least not the normal people like us. We have not understood the difference between high pressure, low pressure conditions where you will have high temperature, low temperature. So insolation here is received almost equally depending upon the position of the sun. So when you have the case of, let's say, the summer solstice, Kishan, now let you tell me, when you have the conditions of summer solstice, which particular latitude receives maximum insolation of sun? That is on 21st of June. Let me know. I'm asking about the exact latitude, Kishan. Line of Cancer, Tropic of Cancer. During the winter solstice, that is 21st of December, which particular latitude receives direct rays of the sun? It is the Tropic of Capricorn. So when we talk about, let's say, during the equinoxes happen twice a year. So during both the equinoxes, which region receives maximum amount of solar insolation? Which is it? Let me know. Equator So we have the condition where Tropic of Cancer will receive maximum insolation in one day. Tropic of Capricorn will receive maximum insolation on the other day. In the meanwhile, the sun, as it is transiting, it is the equator which receives highest amount of insolation almost for major parts of year. So on an average, can we take the case that in equator will receive higher amount of solar insolation on an average through the year? It doesn't tell you that on everyday basis equator will receive high insolation. No. On an average, which is the latitude which receives higher insolation? Can we think about it that equator will receive high insolation taken on an average? Is that understood? Or does that not make any sense? Let me know. Now, if the hilltop has more insolation, but even ITCZ is not at equator. See, you might have studied ITCZ. I don't know about ITCZ. We'll come to ITCZ where in the next module. We'll try to learn what ITCZ is. And ITCZ, if it moves, why it moves. Okay? Please have some patience. Here right now you were talking about insolation. Now you are talking about shifting of ITCZ. Then you will come to temperature. If you have doubts which are prevalent up to the portion till now, kindly ask that doubt. Please don't try to, again, I will repeat, please don't try to get ahead of the modules. Why don't we ask questions about how tropical cyclones are formed if we are moving ahead of the modules? Please let us go with the session, and slowly and steadily as we will move ahead, we will come to the ITCZ. We will talk about how the ITCZ moves. We'll talk about what is ITCZ. Okay, but have we covered that till now? It is not so. So again, every day I am repeating that. Today again I am repeating that, and today is the final time that I am repeating that. Never try to move ahead in terms of 5 modules ahead. Okay? Just stick with the portion that we have covered. Any amount of doubt that you have, kindly ask any kind of doubt. But moving ahead, I'm not as intelligent as you guys. When we come to that, it is then that I will gain an information that what is ITCZ. Okay? Now, hilltop has more insolation. It has lower air density, but it's covered by ice and lower temperature. Okay. So in the region of a hilltop, when we talk about a hilltop, Deepak, you have to understand why is it that the temperature is low. So we have studied about positive lapse rate, that as you move higher up in the atmosphere, the temperature starts to drop significantly. We have studied that. So as you move to the hilltop or a mountain top, the temperature will be very, very low, significantly low, which means what? Which means everything will be frozen in that region. Now it does receive higher amount of insolation, but that heat is lost ever so quickly again. Why? Because in that region, the air density is very less. So you don't have any amount of dense air which can trap or retain that heat. Hence, that is lost very, very quickly. Okay, so that is why despite receiving very high amount of insolation, that heat is lost very quickly. Now, other than this, the temperature is also prevailing winds basically means the winds which are in existence in a region. So in any particular area, you have different types of winds which are in existence. Now, when we talk about these winds basically can either cool down a region, these winds can warm up a region. So that is where we have seen warm advection, where you have warm winds coming to a colder area. They will increase the temperature. Cold advection will lower the temperature. Now, the impact of or the temperature that we experience, that is also something which is impacted by the movement of ocean currents. Ocean currents, what are those? So when we talk about, let's say, an ocean current or a movement of an ocean water, so whenever you have movement of ocean water in a definite direction, in a fixed rate, and in a fixed motion also, that is an ocean current. We will study more about ocean currents when we come to the portion of oceanography. Okay, but here just understand, just like in the case of advection we had the wind movement having different temperatures, here also in the case of convection we have different temperature of ocean currents. You have warm ocean currents as indicated here, and you also have the presence of cold ocean currents. Okay, you have the presence of warm ocean currents as well as you have the presence of cold ocean currents. Now, in this case, whichever region experiences warm ocean currents experiences a slightly higher temperature. Whichever region experiences cold ocean currents exhibits a colder temperature. So here when you observe a warm ocean current, it increases the temperature. And whenever we have the cold ocean current, lowers the temperature. Lowers the temperature. Now, in this case, for example, take the case of northern portion of Atlantic, northern Europe. Now, northern Europe, ideally, it is present at high latitude around 60° north. So, ideally, at that latitude, it would have experienced freezing significantly, at least the coastal areas. But the waters and the coastal areas, they tend to remain ice-free. Why? Because you have the presence of warm ocean current in the form of North Atlantic drift. So when we have, for example, northern Europe remains ice-free due to, or for most of the year due to the warm North Atlantic drift. North Atlantic drift. And not the entirety of Northern Europe. Think about it, North Coastal Europe or the Scandinavian coastline. North Coastal Europe. Okay. So these are the various factors which end up influencing the temperature of any particular area. Now, if you have to depict the temperature of any particular region, if you have to depict the global temperature distribution, how will you do that? So for that, we make use of isotherms. Isotherms basically, these are your imaginary lines which end up joining places indicating equal temperature. That is what is indicated by isotherms. So for example, if let's say you have 4 to 5 places, let's say indicating the same temperature, isotherm drawn across them will indicate a kind of a similarity of sorts. So all the places on this isotherm, let's say this is an isotherm of 10 degrees Celsius. So that means it would join all the places exhibiting 10 degrees Celsius. Okay. Now, if I ask you a question, can isotherms crisscross each other? Can the isotherms crisscross each other? Yes or no? Very good. The answer is, as given by good majority of you, the answer is no. Because isotherms indicate the similarity of temperature. Let us assume this isotherm is 10 degrees Celsius isotherm, this isotherm is 15 degrees Celsius isotherm. Okay. Now, places on this isotherm will indicate 15 degrees Celsius. Places on this isotherm will indicate 10 degrees Celsius. What about this place? Will it indicate 10 degree or 15 degree? The same place cannot indicate two temperatures. That is why isotherms will never crisscross each other. Okay. So even in the case of pressure, when we will see about isobars, they will also never be able to crisscross each other. Now, these are your typical isotherms during the month of January, when it is very cold in the northern hemisphere, winter in the northern hemisphere. Now from here, let us take few derivations. Let us have a few understandings. So for example, let's suppose the heating of land and water. Now, what we have seen earlier during winter as compared to land and water, which is going to be colder during winter? What do you think? Land. Thermal difference is the difference of temperature. That is thermal difference. Isotherm is an imaginary line joining places of equal temperature. So we have seen that during winter, land is colder as compared to the water, isn't it? Now, let us observe that. So, by the way, here you would observe various numbers written, minus 25 degrees Celsius, minus 12.5 degrees Celsius, 0 degrees Celsius, 10 degrees Celsius, all of this. So this indicates that on this isotherm, any place which lies is experiencing 10 degrees Celsius. On this isotherm, any place which lies there indicates 20 degrees Celsius. Okay. So here, with that, let us understand a couple of things. Let us draw a line across this latitude. Now let us start observing the temperatures at different places. A, B, C. Okay. Now tell me, temperature at A will be how much? By looking at the image, what do you think is the temperature at A? Look at the isotherm. Good. What is the temperature at B? When you take a look at B, what is the temperature? 0 degrees Celsius. So at the why 0 degree? Because it is the 0 degree Celsius isotherm which passes through it. So it is 0 degree Celsius. So at the same latitude during winter season, which is colder, it is basically the land which is colder significantly. Okay. At the same latitude, the land will be much colder. Now, if I ask you the temperature at sea, it is minus 12.5. Now, C is also a water body. B is also a water body. But C, despite being at the same latitude, is much more colder. Why do you think so? Why do you think so? That at the same latitude, C is much colder as compared to B. What do you think would be the reason here? Good. Very good. Majority of you have given the correct answer. And that is the issue here is that sea is much closer to the land. So when you are surrounded by land in such close quarters, colder land will have an impact on temperature. Yes, there is an impact of ocean currents, but right now we are not aware of that. So because when you will observe that a water body is closer to the land areas, surrounded by land in very close vicinity and very close quarters, there is an influence of temperature of the land on the water body as well. Okay. So that is something which is going to help us understand the complicated concepts such as Indian Ocean dipole as well as Madden-Julian oscillation. And the concept is simple, that when the land gets heated or cooled down, the areas very close to it, the water body is very close to it, they also get influenced by that heating and cooling. Okay? Yes, something like a spillover effect. In the southern hemisphere, if you notice, you will observe that the isotherms are more or less parallel to each other. And that is because here you have a homogeneity in terms of water presence and water distribution. That is where in southern hemisphere the temperature change is very uniform because southern hemisphere is dominated by water. That is why the temperature distribution is very, very uniform. Observe the thermal image. In the month of January, if you will observe how the land areas are much more colder as compared to the water bodies. Water bodies are much warmer. And again, in the southern hemisphere, observe homogeneity of temperature distribution, how temperature changes very, very uniformly. Then in the month of July, observe it is the land areas which are much warmer, water is cooler. And here again, uniformity of temperature distribution because of significant presence of oceans or water bodies. So that is where you will experience or what you will observe as a temperature variation across the entirety of the planet. Now we come to the portion which is referred to as temperature inversion. Now, what is this temperature inversion? In simple terms, it is the inversion of the normal temperature conditions that we experience. That is it. So, reversal of the normal behavior of temperature in the troposphere, that is what is referred to as temperature inversion. So, what is the normal behavior? When we say normal behavior, what is normal behavior? Normal behavior basically means that here, if this is the ground, as you move up, temperature reduces. Temperature reduces. That means what? That means you have warmer air here and you have colder air on top. Right? What is also referred to as positive lapse rate or a normal lapse rate. Now, in this case, generally, under the normal behavior, warm air will try to rise up and the cold air will try to sink down. So under normal behavior, we can also experience vertical mixing of air. Vertical mixing of air is something we can experience here, isn't it? Now, the opposite of it is temperature inversion. So what is opposite of it? The opposite of it is you have colder air at the bottom, warmer air is trapped at the top. Now, in this case, you have negative lapse rate. That is, the normal conditions are inversed, hence the name temperature inversion. Now, in this case, there will be no mixing of air because the warm air is already at top and the cold air is already at bottom. So here you won't come across any mixing of air, which means what? Which means the air is stable. It does not mix. So no mixing, which means stable air. Now, this exact aspect of colder air coming closer to the ground surface, that is caused by variety of factors. In various parts of the planet, it is caused by variety of factors. And that is the classification of temperature inversion as well. So when we talk about temperature inversion, the types of temperature inversion overall, if you will observe, you have what is referred to as surface inversion, what is referred to as subsidence inversion, what is referred to as frontal inversion, and what is also referred to as valley inversion. So you have different types of inversions which are in existence because of how that inversion has been created. Let us take a look at that, how they are formed, and then we will have a better understanding. Surface inversion. So this is observed in winter months. Winter months, when in general the land becomes very cold, gets colder. Now, during long winter nights, the loss of heat is going to be quite significant. Land gets colder. If you have a cloud cover, that cloud cover will in a way inhibit that loss of heat. That cloud cover will retain some heat. That is why ideally cleared skied nights are sufficient condition for this inversion. Now what happens? The land gets very cold. As a result of that, air in contact with the land, gets colder, very cold as well. Okay, let us take a look at that and listen to this carefully. Once if you pay attention, you will understand, you will never face issue in this. So let's consider winter season. Winter season, let's consider the timing of, let's say 4 p.m. Right? Now, the temperature at ground. Temperature at ground surface, let's assume, is 15 degrees Celsius. Now, the air immediately in contact with it will also exhibit a similar temperature, 15 degrees Celsius. The air is in contact. Air in contact. Now, the air parcel, let's say at a height of few kilometers, that indicates a temperature of 1 or 2 kilometers. Let's suppose that indicates a temperature of 7 degrees Celsius. Air above that, let's say higher up, indicates a temperature of 2 degrees Celsius. Okay, this is during 4 p.m. 4 p.m. in the evening. Then night happens, night time falls. And during night, you have nothing but loss of heat, significant amount of loss of heat. So that heat is consistently lost and the ground becomes colder and colder. Let's think about what happens at 3 a.m. in the morning. As cold as it can get. So let's suppose the ground temperature is or has fallen to 2 degrees Celsius. Let's suppose. Now, when the ground temperature has fallen by 2 degrees Celsius, the air which is in contact will also end up exhibiting a temperature close to around 2 degrees Celsius. Right or wrong? Air will also experience a temperature of around 2 degrees Celsius, which is in direct contact with the ground because of conduction. If a surface is hot and air is in contact with it, the air will also get hot. If the surface is very cold, the air will also get very cold. So at the region of the ground surface, the air will indicate 2 degrees Celsius. So observe that near the ground surface, the temperature has fallen from 15 degrees Celsius to almost 2 degrees Celsius. Now, do you think at this elevation, do you think the rate of fall will be similar where we observe 7 degrees? Do you think the rate of fall of temperature will be similar or will it be different? It will not be similar. Why it will not be similar? Because the lower portion has cooled down at such a rate only because it is in contact with the ground surface. No other reason. If it would have been 1 meter above, the temperature would have indicated a difference. So because the ground has become so cold and it is in contact with the ground surface, that is why it has become so cold. But here higher up, it will not follow the same trend. It will cool down, but not at the same rate. Let's say it cools down to 3 degrees Celsius. From 7, it has cooled down during the night. It has become 3 degrees Celsius. This has cooled down, let's suppose, minus 1 degree Celsius. Now, everywhere the temperature has decreased. But the temperature has decreased very drastically near the ground surface. Why? Because the surface has cooled down. And that has created, observe, colder air, warm air, and that is a condition of inversion. So experienced during long winter nights where you have clear sky. This is experienced in the northern portions of India. Southern portion of India rarely does experience this. So here, a surface inversion occurs when the atmosphere at the Earth's surface is colder than the layer above it. Around sunset, the ground cools very rapidly by radiating heat upwards in the form of terrestrial radiation. The air in contact with the ground cools down by the process of conduction, causing the lowest layer of the air to be cooler as compared to the higher layers. That is the condition of inversion. After that, we come across what is referred to as upper air or subsidence inversion. And here this involves the principle of adiabatic compression. We have studied that whenever you have adiabatic compression, that will always lead to heating. Always. It will initiate heating. So understand this. This is generally observed in middle to high latitudes. Generally, mid to high latitudes. Not observed in India. This is not observed in India. And that too during winter. Winters. So suppose you have the ground surface here. Okay. Now you have, due to air circulation, let's suppose there is a convection current somewhere and air is sinking down in this region. Let's suppose. Meanwhile, the air near the ground surface, air near the ground will be very cold, isn't it? Ground is going to be very cold. So air near the ground surface will also be very cold. Why the ground will be very cold? Because we are talking about mid to high latitudes, and that too during winters. So the air will become cold. Now, if suppose there is sinking air, due to atmospheric circulation, there is a kind of a sinking air. Now, when the air is sinking, it is moving to a region which has got lower density of air to a region which has got higher density of air, isn't it? So it will undergo compression. So there is a compression, and compression leads to heating. So this air will become warmer, warm air. And once it becomes warmer, even let's say 0.1 degree Celsius higher than the lower region, air will not sink anymore, because warm air tends to stay at top, cold air tends to stay at the bottom. So that is the condition of inversion. But here the inversion has happened. Why? Because there was subsidence happening in that region. That is why. So that is where it is referred to as upper air or subsidence inversion. So when a widespread layer of air starts descending, it leads to subsidence inversion. The resulting increase in atmospheric pressure leads to heating and compression. And as a result of that, you have a higher temperature, warmer air is created. Observed across the region of northern and central Europe primarily. Then we have the frontal inversion. Right now, we have not taken a look at what do we mean by fronts. But just to give you a very brief background about it, when we talk about fronts, these are those particular interactions where the cold and the warm air, they will interact, they will meet. So there's a zone of transition which is created, and that is what is referred to as a front. In general, if I ask you, which will have greater volume, colder air or warmer air? What do you think? Which air parcel will have greater volume in general? Good. Always, warmer air will have a greater volume. Colder air will have lesser volume because the particles, they are very close to each other. So when we have the colder layer, cold air in general, we'll study much greater detail about it, so don't fret about it as of now. And let's say we have warm air, much greater volume. When they interact, rather than mixing like good friends, here warm air starts climbing. As if the cold air is an inclined plane, the warm air simply starts rising up. So after some time, the warm air will reach here. So in this particular portion, if you observe the temperature, you have colder air at bottom, warmer air at top. That is the condition of frontal inversion. This is again observed in middle latitudes. Mid latitude means area around 35 to 40 degrees north, 35 to 60 degrees north and south. So that is where it is referred to as mid latitude. Then we have another type of inversion, the last kind of inversion which we'll cover, and then we'll end the session. That is the valley inversion. What is this valley inversion? So it is observed at the valley bottom, during nights, during night. How is it created? Why is it created? So when we talk about, let's suppose a valley. In all the inversions, Tara will have a negative lapse rate. Let's suppose we have the condition of a valley. During night, if I ask you that where is it that you will find warmer air to be present? Will you find the warm air to be present on top of mountain tops during night, or warm air to be present at the valley bottom? Think about it. Good. During night, as the surface loses heat, mountain tops will lose heat very quickly. So you will have colder air on mountain tops and warmer air at the valley bottom. Here you will have warmer air at the valley bottom, and you will have very cold air at top. Cold air. Now, cold air is generally heavier, isn't it? Because the particles are very close to each other. So cold air is very, very heavy. And this cold air, owing to the weight and owing to the force of gravity, automatically starts coming down, sliding down. It slides down. Whatever warm air was present is forced to rise up, is forced to uplift. And the cold air displaces it. So here, cold air displaces the warm air at the valley bottom. And that causes inversion. Okay, so the cold air, basically what happens is, cold air being the heavier one, it will start sliding down the slope due to gravity. It will simply push up that warm air which is present. and that is where you have the occurrence of inversion. That is why wherever you have narrow valleys, it is never prescribed, never advised to stay at the valley bottom or take shelter at the valley bottom during night. That is why in the case of narrow valleys, you will observe people living across the slopes of the mountains rather than valley bottoms, because it becomes so cold at night, oftentimes frosting happens. The plants, they die due to that low temperature. Okay. If let's say this air is allowed to pass or flow by a passage or a kind of an air drainage, then that inversion won't be that dangerous. But if it is a narrow valley, restricted valley, it will have a very dangerous impact. Okay. Frontal inversion basically was when you have cold air and warm air which meet. Cold air being the heavier one will stick to the ground, warm air will rise up. So in that region, you have the formation of an inversion condition. Okay, right? Now I'll give you a particular portion about map pointing, guys. So kindly do this map pointing. Okay. Doesn't the warm valley heat up cold air which is subsided? No, not significantly. It will be very cold when it is coming down. So it won't be heated to that extent. Okay. So here last time we had done the portion about the various mountains. Now I want you to mark certain deserts and certain other features, physical features. So here mark the region of Ozark Plateau. Mark the area of Colorado Plateau. Mexican Plateau. Look at the region of the Gulf of Mexico. Then all these, by the way, North America. Then look at Sierra Nevada Desert. Then after that, this is also in North America. Atacama Desert. Okay. Look at Kalahari. Then look at Victorian Desert. Then certain water bodies. Locate the region of Gulf of Bothnia, Baltic Sea. Then Aegean Sea, Bay of Biscay, North Sea, Sea of Marmara, Azov Sea. Locate these areas. All of these are present in the same region, in the region of Europe. Locate this. Okay. So that is where we'll end the session today. We'll have these questions for discussion on Monday. Okay. We will get these questions for discussion. And a couple of questions I'll pick up. Doesn't still the warm. Okay, that is something I have taken. Gulf, we will. So Gulf is a water body surrounded by land with a very narrow opening. That is a Gulf. Insolation with regards to Tropic of Cancer and Tropic of Capricorn. So basically, what it means is that when you have, think about it, that here you have the presence of the sun and the planet moves around it in an elliptical orbit. And as the planet moves, it has different inclinations. So in, let's say, during the summer season, the inclination of the planet is such. During the summer season, it is the northern hemisphere which is tilted. So if this is the Tropic of Cancer, 23 and a half, on 21st of June, direct rays of sunlight will be received here vertically. So that is where we say that the sun shines vertically over Tropic of Cancer on 21st of June. And then example, when we will, when we talk about, let's say during, okay, I'll bring it back here. So when we talk about the portion of, let's say, the winter season, the tilt will be such that the solar rays will be perpendicular to Tropic of Capricorn. Okay. Is surface inversion also responsible for fog? Yes, it is. How magnetic field obstruct the occurrence of auroras in the lower latitude. So basically, wherever you have the greatest density of magnetic field, that is where these charged particles will be attracted. In the region of the lower latitudes, these magnetic fields, they are not very dense. They simply are moving from north to south. In the northern region, that is where majority of that magnetic field is concentrated around. That is why, if you want, if you are interested enough, if you want to explore more about the auroras, I have done one of those videos on YouTube some time back. You are free to explore that on Baiju's YouTube channel, where it will be with the name of Space Hurricanes. Okay, take a look at this particular YouTube channel and or this particular YouTube video. This is under our YouTube channel, that is Baiju's IS. You'll gain an idea about how, for example, if in these lights, auroras, we observe green, blue, pink lights, why do we observe so? How is it that oxygen reacts? How is it that nitrogen reacts? All of that, you will get to know about that. So you can explore that, provided if you have time. Question in temperature distribution on map. Why a lot of concentration of temperature on Arabian plate? Let me get back to the temperature distribution map so that I can help you out. Here. Okay, this portion you are saying, this particular portion you are referring to. See, the month is July. Now, Kishan, because you are aware of the ITCZ and the concept of ITCZ, this is the particular portion which receives absolutely limited amount of rainfall. So as a result of that, it is here where the absolutest or the most lowest of temperature is to be observed. These are large desert areas. It is here where you have the large desert in the form of Rub al Khali, which gets very heated up. And the wind movement also at this point of time doesn't help. This entire portion in general, that is devoid of rainfall because of the conditions of high pressure, which we will study on Monday, that develops in that region. Okay, I hope that is clearer. Ashish, how to remember all places with example? So see, it is going to be a slow process, my dear friend. So have realistic expectations. Right now, let's suppose you are covering the portion of climatology for the first time. It is absolutely impractical to have the expectation on yourself that immediately everything will be ingrained. Slowly and steadily. That is why I am wanting you to, or I'm forcing you to explore the atlas. Explore the atlas. Look at the regions nearby. When I'm asking you to look at Azov Sea, I hope, and when you are taking a look at, let's say, Sea of Marmara, I hope that you are able to take a look at the surrounding region of the conflict-torn Ukraine-Russian region. And there you will get an idea about why this particular path or straight is important. So slowly and steadily, as more areas across the map you get familiar with, you will always be able to cite as many examples as you can. Map pointing, see, in geography, when we are talking about map pointing, it is going to help you have a better spatial awareness about the various regions which are present. Okay. So, see, right now, please don't get concerned about one of the or the map pointing questions which are asked in prelims. That is largely concentrated around current affairs. Okay, so that is largely concentrated around current affairs. I'll tell you how to tackle that, how to deal with that, what kind of questions to expect there. As of now, I want you to look at these areas in the atlas and just explore these the surrounding regions as well. Okay. Okay, Nisarga, I will keep that in mind. Thank you for correcting me. And Madhur, hi to you as well. So that is where we'll end the session here today, guys. I hope this weekend has been helpful and fruitful to you. We meet again on Monday. Tomorrow, there will be a set of objective and subjective questions which shall be uploaded on the app. Kindly refer to those questions, attempt those questions, get an idea about what are the areas where you are lacking or what are the areas which needs improvement. So till we meet again on Monday, all the best, relax, try to revise. Goodbye. Thank you.